What if the Earth itself began to breathe in rhythm with something not of this world? In early 2025, satellites over both poles detected a pulse, an eerie, synchronized flicker in the auroras. North and south, light rose and fell together, every few seconds. At the exact same time, the interstellar object known as 3IATLAS passed near Earth's orbital plane, emitting faint magnetic fluctuations that no one could fully explain. Solar activity was quiet, the solar wind calm, and yet our planet's magnetic heart seemed to echo a signal from deep space. Coincidence? Or communication through a medium we barely understand? Light and magnetism as the universe's hidden language? Tonight, we'll follow the data, the patterns, and the scientists who admit, off record, that this green pulse may not be random at all. Stay until the end, because what you'll see might redefine what connects worlds across the void. Strange synchrony detected. It began as a flicker, subtle, rhythmic, and almost too symmetrical to be natural. In early May 2025, multiple satellites monitoring Earth's auroras picked up something that made scientists sit up in disbelief. The shimmering curtains of light over both poles, the Arctic and Antarctic, were pulsing in unison. Not random fluctuations, not the chaotic dance usually dictated by solar wind turbulence, but a synchronized heartbeat that repeated with mathematical precision. Instruments from NASA's Themis mission, ESA's Swarm constellation, and Japan's satellite all recorded the same pulse, a steady rhythm at roughly 0.15 hertz. That's one beat every 7 seconds. Auroras don't usually do that. They are messy, unpredictable, driven by bursts of charged particles from the sun colliding with atoms in the atmosphere. But on that day, the pattern was global, stable, and strangely musical. Like Earth itself was responding to a metronome beyond the solar system. Across both hemispheres, the magnetic field oscillated in sync. Magnetometers in Greenland, Antarctica, and even equatorial regions registered faint sympathetic vibrations, forming a planetary pattern that no known solar or atmospheric phenomenon could explain. At first, scientists assumed it was an instrumentation glitch, a cross signal, data contamination, or calibration issue. But that explanation fell apart when independent ground observatories confirmed the same pulse visually. Time-lapse footage from Iceland, Canada, and the South Pole all revealed identical flickering intervals. Even more disturbing, the fluctuations occurred during a period of solar quiet, when auroras shouldn't have been active at all. No major coronal mass ejections, no geomagnetic storms, nothing that could explain such intense global activity. What could make the planet's polar lights beat in rhythm across thousands of miles? The leading hypothesis was electromagnetic resonance, some natural oscillation of Earth's magnetic shell, triggered by a wave from deep space. But as data analysts layered the auroral pulse timeline against other cosmic events, a chilling coincidence emerged. The rhythm matched, almost perfectly, a magnetic fluctuation detected days earlier from a distant traveler, the interstellar object known as 3IATLAS. That object, already famous for its unusual brightness and hyperbolic trajectory, was passing through the inner solar system at the exact same time. Days before the auroral pulses began, 3IATLAS had encountered a massive coronal ejection from the sun. Solar probes captured the collision, a flash of plasma engulfing the green glowing body, scattering ionized fragments into space. The event was cataloged but dismissed as an interesting footnote. No one imagined its effects could echo across 150 million kilometers to Earth. Yet here it was, a repeating frequency linking both events, precise to fractions of a second. Something about that impact, or the object itself, seemed to have released a periodic signal that resonated with Earth's magnetosphere. Some scientists speculated it could be a form of magnetic coupling, energy waves traveling through the solar wind like ripples on an invisible ocean. Others whispered about more exotic possibilities: interstellar resonance, electromagnetic interference, even an unknown plasma phenomenon transmitting through the heliospheric current sheet. The deeper analysts dug, the stranger it got. The pulse wasn't constant. It strengthened at precise intervals corresponding to Earth's rotation, as if the planet's alignment with the object influenced its intensity. When Earth's night side faced 3IATLAS's trajectory, the pulse peaked. When the object dipped below the ecliptic, it weakened. It was almost as if Earth and the interstellar visitor were locked in a silent, rhythmic exchange, a heartbeat shared across the void. The auroras themselves reflected this hidden conversation. Eyewitnesses in Alaska and Norway reported patterns unlike anything they had seen. Vertical waves of green light appearing and vanishing with the rhythm of breath. Some described it as watching the sky inhale and exhale. In Antarctica, scientists at the Amundsen-Scott station documented the same cadence. When they compared footage from both poles side by side, the symmetry was undeniable. The peaks and fades occurred simultaneously, separated by half the planet's diameter, yet perfectly aligned in time. Mainstream outlets didn't report much. The data was too strange, too easily dismissed as coincidence. But within research circles, encrypted messages began circulating. Auroral sync confirmed, cross-polar correlation verified, check solar archives for repeating modulation. A few dared to ask the forbidden question: could 3IATLAS be generating a signal, intentional or not, capable of influencing planetary magnetism? The idea sounded absurd, and yet the numbers refused to cooperate with skepticism. Meanwhile, magnetometer stations around the world began noticing side effects. In certain latitudes, compasses wavered minutely at the same rhythm as the auroral pulse. The fluctuation was weak, barely measurable, but it existed. Even seismometers picked up faint periodic noise, suggesting a coupling between electromagnetic oscillations and the lithosphere. That shouldn't happen, but it did. As the weeks went on, the pulse faded, then returned sporadically. Each recurrence seemed linked to shifts in the interstellar object's trajectory as it neared the ecliptic. And each time it returned, the synchronization between hemispheres tightened, as though the planet itself were tuning to an external frequency. It's tempting to dismiss all of this as coincidence, data overlap, algorithmic noise, human pattern seeking. But the timing defies easy dismissal. The pulse began within 24 hours of 3IATLAS being struck by solar plasma and ceased exactly when the object's induced magnetic tail collapsed. Scientists at ESA's Space Weather Center privately admitted that no other solar or cosmic variable lined up so neatly. In an internal memo leaked later that month, one researcher wrote, "We can't explain it using current magnetospheric models. Something external is modulating Earth's field." Speculative forums exploded. Some claimed the interstellar visitor acted like a cosmic tuning fork, channeling solar energy into harmonic frequencies that Earth's field naturally resonated with. Others compared the phenomenon to Schumann resonances, those low-frequency electromagnetic waves trapped between the ground and ionosphere, but on a planetary scale, amplified by an unknown driver. The most unsettling theory suggested the pulse wasn't simply a reflection of energy, but a response. That something in Earth's magnetic structure had recognized the incoming frequency and synchronized with it. To those who study space weather and magnetodynamics, that idea borders on heresy. Yet history is filled with anomalies, periods where auroras behaved in ways physics couldn't fully explain. The Great Aurora of 1872, the luminous waves of 1941, even the synchronized substorms of 2015, all mysteries that faded into scientific footnotes. But the green pulse felt different. Its timing with an interstellar object, its rhythmic precision, its global symmetry, all unprecedented. If it was a coincidence, it was one of cosmic proportions. If it wasn't, it hinted at a deeper link between celestial events and Earth's electromagnetic soul. And so, as 3IATLAS continued on its path, vanishing into the black beyond Mars, the world's instruments kept listening. For some, the data looked like a warning, evidence that forces beyond our comprehension can whisper directly into the magnetic heartbeat of our world. For others, it was an invitation to look deeper, to question what natural really means in a universe that may be far more interconnected than we've ever imagined. Because once you see a planet's lights pulse in time with something from the stars, you can't help but wonder, what else out there is listening back? Instrumentation and data oddities. The first whispers of an anomaly didn't come from the sky, but from the instruments built to read it. In early May 2025, engineers at NASA's Goddard Space Flight Center began noticing irregularities in magnetometer outputs across multiple satellites. At first, they assumed it was noise, cosmic interference, solar wind distortion, or even a simple calibration drift. But when identical fluctuations appeared in data streams from entirely different spacecraft orbiting in opposite hemispheres, it became clear something else was happening. The initial alert came from ESA's Swarm constellation, a trio of satellites designed to map Earth's magnetic field in exquisite detail. The onboard vector field magnetometers began registering rhythmic oscillations, small, periodic swings in magnetic intensity that repeated every few seconds. Engineers ran diagnostics: no hardware errors, no clock desynchronization, no spurious signals from onboard electronics. Everything checked out. Then the same oscillation appeared in NASA's Themis data, a mission tasked with studying auroral dynamics. Themis A, orbiting near the dayside magnetopause, and Themis D on the night side both detected magnetic field undulations that matched the swarm readings to within milliseconds. Normally, magnetic waves generated by solar activity take minutes to travel across the magnetosphere. These signals appeared instantaneous, mirrored across hemispheres as though Earth's entire magnetic field were vibrating in unison. Even more puzzling, JAXA's Auroras ERG satellite, operating in the inner magnetosphere, picked up subtle flux variations at the same frequency, around 0.14.16 Hz. This wasn't background noise. It was clean, consistent, coherent. The amplitude rose and fell cyclically, producing a waveform that looked artificial in its precision. "It's almost too perfect," one ESA engineer remarked in a private channel, like someone's feeding a carrier signal through the ionosphere. Ground observatories soon joined the puzzle. The SuperMag network, an array of magnetometers spanning more than 300 stations worldwide, confirmed identical rhythmic fluctuations in the horizontal magnetic field component. From Svalbard to Antarctica, from Alaska to Tasmania, the pulse was there. What baffled scientists most was its synchrony. In geomagnetic events triggered by solar storms, magnetospheric oscillations ripple outward, delayed by distance. But in this case, the delay was zero. Every station saw the same up and down motion of magnetic intensity, repeating with machine-like regularity. When plotted in spectrograms, the pattern formed a striking image: a vertical line across multiple frequencies, as if Earth's entire field had been struck like a bell. The oscillation wasn't chaotic, like ordinary alpha waves. It was coherent, monochromatic, and sharply bounded. In physics terms, it behaved like a forced resonance driven by an external periodic source. At the Finnish Meteorological Institute, data analyst Alina Vartiainen double-checked her algorithms, convinced she'd found a processing artifact. When she compared it with raw telemetry from ESA's magnetic payloads, her stomach dropped. The signal was real. "It's in the original field readings," she wrote in a memo. "It's everywhere. We can't find a source inside the system." The mystery deepened when atmospheric data was overlaid. The ACE and DISCOVER satellites, both stationed at the L1 Lagrange point to monitor the solar wind, showed no anomalies. Solar wind speed was stable. Plasma density and interplanetary magnetic field orientation were normal. In other words, nothing from the sun should have caused this. And yet, Earth's magnetic cocoon was rhythmically vibrating without a known driver. Some theorized a software synchronization bug, perhaps an identical clock drift in satellite telemetry, creating the illusion of periodicity. But the onboard systems ran on independent timing references, each cross-calibrated against atomic standards. The odds of multiple spacecraft from different agencies, all manifesting the same artificial signal simultaneously, were astronomical. Others suggested electromagnetic interference from terrestrial sources, power grids, radio transmitters, or radar arrays. But the global pattern ruled that out immediately. The oscillation appeared even in remote Antarctic stations and deep ocean observatories, where man-made EM noise was negligible. That's when researchers at Stanford's VLF research group stepped in. They had long monitored the Earth ionosphere cavity for extremely low-frequency LF waves, natural resonances known as Schumann frequencies. Those frequencies typically occur at 7.83 Hz and harmonics thereof, far higher than what was being detected. But curiously, the new oscillation wasn't random background. It seemed to modulate the existing Schumann resonances, imprinting a beat pattern that made the data look alive. When overlaid on auroral imaging from the POES and DMSP satellites, a strange synchronization appeared. Each auroral brightness surge coincided with the downward phase of the magnetic oscillation. In simpler terms, the lights brightened as the magnetic field contracted, then dimmed as it relaxed, a breathing motion visible in both hemispheres. At NOAA's Space Weather Prediction Center, scientists began referring to it informally as the heartbeat anomaly. Internal chat logs leaked later showed growing unease among analysts. Open quote, "Is there a shared driver we're missing? Could this be a deep magnetospheric mode excited by something external? It's showing up on multiple independent data sets. That's unprecedented." And close quote. Around this time, the coincidence with 3IATLAS was first noticed. A data engineer cross-referencing timestamps between the auroral pulses and deep space magnetometer readings from NASA's Parker Solar Probe noticed something uncanny. Just hours before the first Earth-based oscillations began, Parker recorded a faint, periodic magnetic fluctuation propagating outward from the Sun, a remnant of a coronal mass ejection that had directly impacted the interstellar object 3IATLAS. That CME, cataloged as Event 25142, had shown an unusual waveform, with a decaying oscillation pattern nearly identical to the frequency later observed around Earth. To most space weather analysts, this was coincidence, but to a few data scientists, it was a smoking gun. The waveform shape matches within error, one wrote in a restricted Slack thread. If it's coincidence, it's the best imitation I've ever seen. Data audits began in earnest. Engineers pulled telemetry archives, checked clock alignment, cross-compared reference points. The more they tried to eliminate errors, the clearer the pattern became. The oscillation wasn't in the instruments, it was in the environment. Even instruments not designed for magnetism picked it up. The Gracefo gravity satellites detected subtle accelerometer oscillations at the same rhythm, possibly caused by variations in ionospheric density. Seismic arrays in Japan reported a weak periodic background vibration in the upper crust, so faint it was near the threshold of detection, yet statistically significant when stacked over hours. By late May, internal briefings circulated under the heading Cross-Polar Magnetospheric Coupling Event, CPMCE 2025. The memo noted, unexplained synchronous oscillation in the geomagnetic field observed across 90% of magnetometer network. Frequency range, 0.14 to 0.17 Hz. Duration, variable, 5 to 40 minutes per event. Source, undetermined. In private discussions, some experts speculated about an external electromagnetic driver, perhaps a standing wave in the interplanetary magnetic field induced by 3IATLAS's interaction with solar plasma. Others went further, suggesting the interstellar object might possess residual magnetization, acting like a tuning fork struck by the sun's coronal blast, sending ripples through the heliospheric current sheet that reached Earth days later. Whatever the cause, the signature was too clean to ignore. Data visualizations revealed perfect phase alignment between northern and southern hemisphere measurements. No lag, no scattering. It was as if an invisible field encased the planet, pulsing with steady rhythm, binding both poles in a single electromagnetic breath. By June, the phenomenon began to fade. Satellite readings returned to normal, but the data left behind a trail of questions. Why did so many independent sensors record identical fluctuations? Why was the waveform so pure, free of random noise typical of space plasma dynamics? And how did it manage to bridge hemispheres with zero delay? When researchers at Kyoto University ran Fourier analyses on the archived signal, they discovered something even stranger: faint harmonics nested within the main frequency. Overtones separated by exact multiples of 0.015 Hz. Natural processes rarely produce such harmonic precision. Artificial systems do. The findings sparked heated debate. Was the pulse an interference artifact from human activity, or an emergent resonance created by a cosmic driver? Attempts to reproduce the signal in simulation failed. No combination of solar wind variations, magnetospheric instabilities, or field-aligned currents could produce the observed coherence. In the absence of an explanation, some institutions quietly labeled it a non-repeating anomaly, but others refused to let go. Today, the green pulse remains archived under a cryptic tag in several mission datasets. Event ID 3I coupling 25. To most, it's a curiosity. To a few, it's a hint that Earth's magnetic field is not just reactive, but receptive, that the instruments didn't malfunction. They simply caught a whisper from something larger, something resonating far beyond our understanding. And if the synchronization between our machines and the planet itself was real, then perhaps what they measured wasn't interference at all. Perhaps, for a moment, the instruments became part of the phenomenon, recording not noise, but a message written in magnetism. Baseline Aurora Science. To understand just how strange the green pulse was, you first have to understand what auroras are and what they aren't. For all their beauty, auroras are not mystical. They're physics in motion. Every flicker of green, red, or violet light in the polar skies begins 150 million kilometers away at the sun. There, solar storms hurl charged particles, electrons and protons, into space. These particles stream outward in the solar wind, invisible but relentless, traveling at hundreds of kilometers per second. When they reach Earth, they slam into our planet's magnetic shield, the magnetosphere, which diverts most of them harmlessly aside. But at the poles, where magnetic field lines dip inward, some of those particles spiral down into the upper atmosphere. That's where the light show begins. When high-energy electrons collide with atoms of oxygen and nitrogen, they excite those atoms, temporarily pushing their electrons to higher energy states. As the atoms relax back to normal, they release photons. Oxygen tends to glow green at around 557.7 nanometers, sometimes red at 630.0 nanometers. Nitrogen adds blues and purples. Together, they create those shimmering veils that dance across polar skies. The patterns we see, curtains, spirals, coronas, aren't random either. They trace the invisible lines of Earth's magnetic field, painting its geometry in light. Auroras ripple when geomagnetic storms fluctuate. They twist when solar wind pressure changes. They brighten when bursts of plasma, called coronal mass ejections, reach Earth's magnetosphere and dump energy into it. That's the normal picture. Beautiful, complex, but predictable in a broad sense. The auroras follow the sun's moods. When the sun is calm, auroras fade. When the sun erupts, they surge. No mystery there. But what happened during the green pulse defied that basic rule, because the sun at that moment was unusually quiet. To put that into perspective, during a typical auroral storm, solar wind speeds might rise from 400 to 700 kilometers per second, magnetic field strength increases, and Earth's KP index, a global measure of geomagnetic disturbance, shoots above 5 or 6. Yet on the nights when the auroras began pulsing in rhythm, the solar wind speed hovered at 370. The KP index stayed below 3. Solar X-ray flux, usually a sign of flare activity, remained flatlined. In other words, nothing from the sun explained the intensity or timing of the displays. The anomaly wasn't subtle either. Normally, auroral arcs shimmer irregularly, their brightness modulated by turbulence in the magnetosphere. But in May 2025, both the northern and southern ovals began to brighten and dim at perfectly synchronized intervals, every 7 seconds, like the beat of a cosmic metronome. In high-speed imagery, it looked like the sky was breathing. Scientists scrambled to reconcile the phenomenon with known auroral physics. One explanation proposed a standing wave forming in Earth's magnetotail, the long extension of the magnetosphere trailing away from the sun. Plasma waves there can oscillate periodically, and if they couple to field lines near the poles, they might cause auroral modulation. But for that to happen simultaneously across both hemispheres, that would require an external driver of extraordinary symmetry. To probe the mystery, research teams revisited the fundamentals. The magnetosphere is a vast, invisible bubble carved into the solar wind by Earth's own magnetic field. It stretches tens of thousands of kilometers into space, compressing on the sunward side and trailing off like a comet tail on the night side. Within this region, charged particles don't move freely. They spiral along magnetic field lines, bounce between mirror points, and occasionally leak into the atmosphere to produce auroras. At its simplest, the magnetosphere acts like a resonant cavity, capable of vibrating when struck by external forces, just as a bell rings when hit. Scientists have cataloged dozens of such vibrations: ULF waves, ultra-low frequency, Alfvén waves, field line resonances. These oscillations can influence auroral structures, causing waves or flickering patterns that align with the rhythm of the magnetic field. But those known modes occur at specific frequencies, or 0.001 to 0.05 Hz, often localized to one hemisphere or magnetic latitude. The green pulse's 0.15 Hz oscillation didn't fit any known resonance category. It was faster, global, and symmetrical. No known magnetospheric process can produce a perfectly mirrored response at both poles simultaneously without delay. That symmetry became the heart of the mystery. Normally, the north and south auroral ovals respond differently because the interplanetary magnetic field IMF connects to Earth at different angles in each hemisphere. This asymmetry is well documented. A southward IMF intensifies northern auroras more strongly. A northward IMF does the reverse. Never in recorded history had both hemispheres produced perfectly matched oscillations at the same instant. To appreciate why that's so improbable, imagine Earth's magnetic field lines as giant elastic strings stretching from pole to pole. When the solar wind hits one side, the strings vibrate, but the motion travels along them at finite speed. Even at Alfvén wave velocities, roughly 1,000 kilometers per second, it would still take seconds for disturbances to propagate between poles. Yet the green pulse's synchrony had zero lag, instantaneous correlation. That defied known plasma physics. Some scientists speculated about magnetic conjugacy, the idea that field lines connecting the two hemispheres could act as transmission paths, allowing simultaneous auroral responses. But that mechanism still couldn't explain why the oscillation frequency matched the magnetic signature detected from interstellar space near 3IATLAS's path. Others proposed a link to PC1 Pearl pulsations, natural geomagnetic waves that sometimes modulate auroras in quasi-periodic patterns. PC1 waves, however, are irregular, their frequencies varying between 0.2 and 5 Hz. The green pulse's frequency was not only steady, but global. PC1 events don't coordinate across hemispheres. There was also the question of intensity. Ground-based photometers in Tromsø and Antarctica recorded synchronized light amplitude changes up to 40%, far exceeding typical flicker levels. To produce that much energy modulation without a solar driver required an unknown mechanism feeding power into Earth's upper atmosphere. In search of analogs, researchers scoured past records. The Great Aurora of 1872, the geomagnetic storm of 1921, the 1989 Quebec blackout, even the Halloween storms of 2003. None exhibited this kind of rhythmic coherence. Those were chaotic, explosive events tied directly to solar outbursts. The green pulse was serene, methodical, almost intelligent. At the Geophysical Institute in Alaska, modeling teams began exploring exotic possibilities. One simulation showed that if an external magnetic field, oscillating at the right frequency, were superimposed on Earth's magnetosphere, it could induce synchronous auroral modulation by coupling through the ring current, a donut-shaped region of trapped particles encircling the planet. But where would such a field come from? The sun was silent. The only other magnetic anomaly in the solar system at that time came from the region near 3IATLAS. Still, mainstream science remained cautious. Correlation, after all, isn't causation, and auroras have surprised us before. In 2016, for example, researchers discovered pulsating aurora patches that appeared and disappeared with near-periodic timing, linked to chorus waves in the magnetosphere. But even those localized pulses bore no resemblance to the global synchrony of 2025. Understanding baseline auroral physics only sharpens how unearthly the event was, because auroras by their very nature are chaotic. They depend on random bursts of electrons, turbulence in plasma sheets, and the constantly shifting dynamics of space weather. They're the opposite of order. Yet during those nights, the heavens behaved like a single, coordinated system, an orchestra following an invisible conductor. One researcher described it best in an internal email. Auroras are usually like jazz, improvised, unpredictable. But this was a metronome. The regularity became its own enigma. Why every 7 seconds? Why both poles? And why during a period of solar stillness? Those questions would drive investigations far beyond auroral physics, into the domain of heliophysics, interplanetary coupling, and even interstellar magnetodynamics. But even before speculation began, there was consensus on one thing. Whatever caused the green pulse wasn't part of the known auroral repertoire. As days passed, citizen scientists uploaded videos comparing northern and southern displays side by side. The visual rhythm was unmistakable. Some observers claimed they could predict each brightening. Others reported feeling faint electrical tingling during peak pulses, a subjective claim, but one that added to the mystique. When researchers reconstructed the magnetic field topology from satellite data, they found the field lines themselves appeared to oscillate slightly, expanding and contracting rhythmically like a breathing lung. The motion was minute, measured in tens of nanoteslas, but enough to modulate particle precipitation and therefore light intensity. That meant Earth's magnetosphere wasn't just responding, it was moving in a periodic way, and movement implies energy input. But from where? If this had been a solar storm, the answer would be simple: the sun. But with solar activity flat, attention turned outward, to the mysterious traveler that seemed to arrive at precisely the wrong, or right, time. 3IATLAS, still glowing faint green in distant telescopes, was crossing near the ecliptic, its tail interacting with the solar wind. Some models showed faint plasma waves radiating outward along heliospheric field lines, theoretically capable of reaching planetary distances. It was a stretch, but it was the only known event in space that matched the timing. And so, auroral science found itself on the edge of something uncomfortable. The possibility that the light dancing above our poles might have been responding not to our sun, but to a messenger from the stars. That notion, whispered at conferences and dismissed in official reports, changed how some scientists viewed auroras entirely. They were no longer just mirrors of solar behavior. They were instruments, sensors revealing how the universe breathes. The baseline science remains solid. Auroras are the language of charged particles and magnetic fields. But in May 2025, that language spoke in rhythm with something alien to our solar system. And once you see that rhythm written across the night sky, pulsing in time with a distant visitor, it becomes impossible to think of auroras as mere weather. They start to look like signals, unusual solar calm. For decades, scientists have looked to the sun as the ultimate clock of cosmic activity. Its flares, winds, and magnetic storms dictate the rhythm of our solar system, influencing everything from satellite orbits to power grids on Earth. But in early May 2025, that clock seemed to stop ticking. The sun fell silent at the very moment Earth's auroras began to pulse. It was a stillness so perfect, so mathematically clean, that it raised more questions than answers. Solar physicists had been tracking Cycle 25 with unusual interest. Forecast models predicted an upswing in activity leading toward the solar maximum expected in 2025 to 2026. Sunspot numbers were climbing, magnetic field reversals intensifying. Yet as the auroral heartbeat appeared, every major solar monitoring instrument, NASA's Solar Dynamics Observatory, SDO, the European Space Agency's Solar Orbiter, and NOAA's GOES satellites reported the same thing: calm skies, no major flares, no coronal mass ejections directed toward Earth, no fast-moving solar wind streams. The solar corona itself, normally a chaotic ballet of plasma loops and magnetic reconnection, appeared eerily stable. In white light coronagraphs, filaments barely moved. The background X-ray flux flatlined. It was as if the sun, for a brief and crucial window, had decided to hold its breath. That's what made the green pulse so perplexing. Normally, when Earth's auroras surge or flicker, space weather forecasters can point to a solar driver, a flare's energetic protons, a CME's magnetic shock front, or fluctuations in the interplanetary magnetic field, IMF. But on May 5th, 6th, and 7th, the precise dates of the synchronized auroral rhythm, all those parameters stayed neutral. Solar wind speed averaged 368 kilometers per second, IMF strength hovered at 4 nanoteslas, and particle density remained steady at around 6 protons per cubic centimeter. NOAA's KP index, which quantifies geomagnetic activity on a scale from 0 to 9, didn't rise above 3. Under normal conditions, that's the kind of quiet day when auroras barely reach the Arctic Circle. Yet during those same hours, satellites recorded bright, structured auroras visible as far south as Scotland, Alberta, and southern New Zealand. Something wasn't adding up. At NASA's Space Weather Center in Maryland, analyst Miguel Ortega cross-checked every data stream he could find: ACE, Discover, Stereo A, even aging SOHO telemetry. There was nothing, he later said in an internal memo. No coronal holes, no solar wind shocks, no sector boundaries. The magnetosphere was calm, but the ionosphere wasn't. It's like the top of the atmosphere was responding to a signal the sun didn't send. To understand how unprecedented this was, you have to look at how dependent auroral activity is on solar variability. Even small changes in solar wind pressure can trigger dramatic effects in Earth's magnetic tail, generating substorms and colorful displays. But those effects require input, fluctuations in density, velocity, or direction. During the green pulse, there were none. Instead, The magnetosphere appeared to oscillate on its own, as if responding to a phantom wave. Magnetometers from both hemispheres traced sinusoidal patterns in field strength perfectly synchronized across continents. In normal conditions, those oscillations would be damped almost immediately without continuous solar input. The fact they persisted, stable, repeating, and global, suggested some form of external or resonant forcing. Solar physicists are trained skeptics. They've seen anomalies come and go, instrument errors, telemetry desyncs, optical illusions, but the timing of this one was impossible to ignore. Just 48 hours before the auroral pulse began, the Sun had ejected a moderate coronal mass ejection toward interplanetary space. Not Earth-directed, but instead heading toward a different target, a faint green interstellar object cataloged as 3IATLAS. When Parker Solar Probe's magnetometer data was overlaid, the CME's residual waveform showed a decaying oscillation at roughly 0.15 Hz, the same frequency later seen in Earth's magnetic field. A few analysts joked that the Sun sneezed at an alien rock and Earth caught the echo, but privately the correlation spooked them. Could the Sun have transmitted an oscillatory signal that somehow resonated across the heliosphere, even though it wasn't aimed at our planet? Could 3IATLAS have reflected or modulated that wave, acting as a kind of interstellar mirror? The idea was absurd by conventional standards, but the data begged for imagination. The solar calm paradoxically became the loudest clue, because in the absence of chaos, patterns stand out. The Sun isn't truly ever still. Even in its quietest phases, it hums with oscillations, acoustic and magnetic vibrations called heliosysmic waves, rippling through its interior like the resonant tones of a massive instrument. Those oscillations produce subtle fluctuations in luminosity and magnetic output, far too weak to trigger auroras on Earth. But if something amplified them, a coupling, a reflection, or a resonance with an external field, they might, in theory, modulate Earth's magnetosphere indirectly. That's when researchers at the European Solar Observatory proposed a radical hypothesis: interplanetary magnetic resonance. If the CME that struck 3IATLAS set up standing waves along the heliospheric current sheet, the vast wavy plane of magnetic flux that connects the Sun to the outer planets, those waves could propagate throughout the solar system, modulating planetary fields like plucked strings. Normally, such waves dissipate quickly in the turbulent solar wind. But Cycle 25's calm created ideal conditions for coherence. With little background noise, any sustained oscillation could travel further and remain stable longer. And when it reached Earth, the magnetosphere might have responded in kind, resonating in sync, producing the global auroral beat we call the green pulse. It sounded poetic, but could physics support it? The problem, skeptics pointed out, was magnitude. The energy required to modulate Earth's entire magnetosphere would be astronomical. The amplitude of the detected oscillation, around 10 nanoteslas, implied a power input millions of times greater than typical interplanetary fluctuations. No known natural wave from deep space could achieve that. And yet, it happened. Meanwhile, solar telescopes recorded something else: a faint, repeating dimming in the corona near the region where the CME had originated. Every 7 seconds, a microvariation in brightness appeared and faded. It was so subtle it took hours of data stacking to confirm, but once seen, it couldn't be unseen. The pattern matched the same rhythm as the auroral oscillations on Earth. Could the Sun itself have been oscillating at that frequency, transmitting energy across the solar system? If so, why had no previous event produced such a coherent planetary response? Some researchers at the time suggested that the answer lay in the solar minimum paradox. During periods of low activity, the Sun's magnetic field can occasionally become globally aligned like a single stable dipole. In that configuration, small perturbations can propagate cleanly without the usual interference of tangled field lines. In other words, the Sun's calm wasn't silence. It was clarity, a moment when the system became resonant enough for subtle interactions to echo far louder than usual. It was this calm, this rare magnetic stillness, that made Earth's response possible. But there was another layer to the enigma. While the Sun's visible face was serene, space weather monitors detected something odd in the solar wind composition: a faint enrichment of ionized nickel and carbon, similar to the chemical signatures later confirmed around 3IATLAS. That hinted that some fraction of the CME that struck the interstellar object might have recoupled into the heliospheric flow, carrying traces of exotic material or altered magnetic topology. What if the sun's calm wasn't entirely natural? What if it was the result of a temporary magnetic equilibrium, induced or stabilized by its inner external magnetic field, perhaps the ones surrounding the interstellar object itself? Those were dangerous questions, the kind that made funding committees nervous and journal reviewers skeptical. But they whispered through the scientific community nonetheless. Because if the green pulse was truly born out of a silent sun, then it meant energy could flow through the heliosphere without the usual violent solar outbursts. It suggested that the sun, planets, and even passing interstellar visitors were connected by more subtle magnetic harmonics than anyone had imagined. The calm before the pulse wasn't absence, it was attunement. In the weeks that followed, the sun resumed its usual volatility. Flares erupted, solar wind speeds climbed, and the synchronized auroral beat faded away. To most, the event became a curiosity. To a few, it became a revelation, because it showed that sometimes the universe doesn't speak in noise, it whispers in rhythm. And that whisper may have begun when the solar system itself fell silent long enough to hear its own heartbeat echo through the void. Enter 3IATLAS. When the auroras began to pulse, Earth's scientists turned their gaze outward, far beyond the sun, beyond even the realm of the planets, to a strange green traveler cutting silently through the void. It was small, faint, and utterly alien in trajectory, an interstellar object cataloged simply as 3IATLAS. It wasn't the first such visitor, but it might be the most enigmatic. Unlike Oumuamua or Borisov, this one arrived bearing signs that something about it didn't belong to ordinary physics. Discovered in early 2025 by the Asteroid Terrestrial Impact Last Alert System in Hawaii, 3IATLAS was first thought to be just another hyperbolic comet, a body passing through the solar system once before vanishing forever. But almost immediately, astronomers noticed things that defied easy classification. Its brightness was unstable, fluctuating in ways that couldn't be explained by rotation or dust jets. Spectrographic analysis showed odd emissions, faint green lines corresponding to nickel, cyanide, and molecular carbon, compounds rarely found together in such abundance. And then there was the color. Most comets glow white, blue, or slightly green due to diatomic carbon. But 3IATLAS glowed a deep, saturated emerald visible even at large distances. Amateur observers joked that it looked like a shard of alien glass drifting through space. Professionals, though, were unsettled by how much light it reflected compared to its estimated size. Its albedo suggested a highly reflective surface or energetic emissions, both rare for a body traveling through interstellar space for millions of years. Its orbit sealed the mystery. 3IATLAS followed a hyperbolic trajectory with an eccentricity of 1.20, too high for any solar system origin. It came from the direction of the constellation Hercules, plunging toward the inner solar system at over 30 kilometers per second. More curious still, it was moving along a path nearly aligned with the ecliptic plane, the flat disk on which most planets orbit. That alignment is statistically improbable for random interstellar visitors. It was as if it had chosen the highway that passes through all major worlds. As it approached, observatories worldwide scrambled to capture data. The James Webb Space Telescope, though designed for distant galaxies, turned its mirrors toward the intruder and detected volatile activity at an unusual distance, far beyond the region where sunlight normally vaporizes ice. That meant it was active too early, releasing gases without the expected thermal trigger. Something within it was driving sublimation long before the sun's heat could. NASA's Solar and Heliospheric Observatory, SOHO, recorded something else, an expanding coma with unusual polarization, light scattered in ways suggesting organized magnetic structures within the dust cloud. 3IATLAS seemed to carry a magnetic field of its own, or at least interact with the sun's in a way no comet had before. Then came the event that tied it all together. On April 29th, a mid-sized coronal mass ejection erupted from the sun's western limb. Most of its plasma missed the planets, except for one small region near the path of 3IATLAS. Hours later, Parker's solar probe detected a ripple in magnetic field strength and a distinct decaying waveform, the same oscillation that would later appear in Earth's magnetosphere. Within a day, telescopes observed a dramatic brightening of the object. It flared in both visible and ultraviolet light, expanding its coma and releasing jets that appeared almost symmetrical, like opposite poles emitting synchronized bursts. Scientists were stunned. Natural outgassing from comets is chaotic, driven by uneven heating and rotation. But 3I-ATLAS's emissions looked ordered, periodic, as if it were responding to the CME that hit it. One astrophysicist at Caltech described the symmetry as uncomfortably engineered. But the real intrigue came when the oscillation frequency of that flare, 0.15 Hz, matched the rhythmic beat later observed in Earth's auroras. Solar-comet interaction. When the sun's coronal mass ejection struck 3I-ATLAS, the event was brief, a cosmic blink, yet the consequences rippled across the solar system. Solar physicists initially logged it as a routine plasma collision, but as the data poured in, routine quickly fell apart. The CME in question, recorded on April 29, 2025, was modest in strength, roughly 600 kilometers per second, with a magnetic flux density peaking at 10 nanoteslas. Nothing extraordinary by solar standards. Normally, such an ejection would dissipate quietly into the solar wind. But as it intersected the position of 3I-ATLAS, something happened that no simulation had predicted. Instruments aboard the Parker Solar Probe and Solar Orbiter, which were then at advantageous angles relative to the event, captured what appeared to be a magnetic rebound. A reversal in polarity and a surge of coherent waves radiating outward from the impact point. Solar physicists stared at the plots in disbelief. When a CME hits a comet, it should distort the tail, compress the ion sheath, and blow off dust, not generate an outgoing pulse strong enough to register across millions of kilometers. The waveform Parker recorded resembled a decaying oscillation, a perfect damped sine wave cycling at roughly 0.15 Hz. That frequency would later match, with eerie precision, the auroral rhythm detected at Earth. But how could a small comet, barely a few kilometers across, reflect or modulate solar plasma on such a scale? The first clue came from magnetohydrodynamic models. Researchers at the Heliophysical Modeling Center ran simulations using data derived from the CME's structure and the presumed composition of 3I-ATLAS. Under normal conditions, a comet's magnetic interaction is limited to its magnetotail, the induced field formed by ionized gases flowing away from the nucleus. However, the model couldn't replicate the waveform unless the comet possessed an intrinsic magnetic field. That alone was staggering. No comet previously observed had ever shown definitive evidence of internal magnetism. Even 67P/Churyumov-Gerasimenko, studied up close by ESA's Rosetta mission, had essentially zero magnetic remnants. But 3I-ATLAS, if the model held, seemed to respond like a conductor, as though it contained ferromagnetic or superconductive material capable of channeling current. Solar Orbiter's heliospheric imager then picked up something stranger. In the hours after the CME's impact, the plasma around 3I-ATLAS formed what looked like standing waves, concentric ripples of charged particles oscillating symmetrically from the body. This wasn't a typical bow shock or tail deflection. It was organized, rhythmic, and persistent. Observers began calling it the magnetic shell, though no one could agree whether it was cause or effect. Meanwhile, back on Earth, ground-based observatories detected the comet's brightness surge. Its apparent magnitude jumped from +12 to +7 in under 6 hours, a 5-magnitude leap, representing a 100-fold increase in luminosity. Spectroscopy revealed a temporary dominance of ionized nickel and carbon compounds, materials that shouldn't survive prolonged exposure to interstellar radiation. They glowed intensely green, as if the object were suddenly alive with internal current. For comparison, when the sun's plasma struck comet Anke in 2007, its tail broke off completely, a textbook disconnection event. But 3I-ATLAS didn't lose mass. It seemed to absorb and re-emit energy, converting the CME's shock into electromagnetic waves of near-perfect periodicity. At the European Space Astronomy Center, plasma physicists tried to understand how such conversion could occur. The working theory centered on magnetic reconnection, the process by which magnetic field lines snap and realign, releasing energy. If 3I-ATLAS possessed an intrinsic field opposite the sun's at the moment of impact, reconnection could have injected enormous electrical currents into its coma. Those currents, in turn, could generate oscillations, the kind of rhythmic waves that radiated outward and, eventually, reached Earth. But the precision of the signal baffled even the most seasoned modelers. Nature rarely produces such clean frequencies. Plasma turbulence should have smeared the oscillation into noise, yet the pulse remained coherent for hours. Some theorists began whispering about parametric resonance, the idea that the solar wind itself, driven by oscillations in the sun's magnetic field, could synchronize with the comet's internal magnetism, amplifying it like two tuning forks vibrating in harmony. As the CME passed, Parker recorded another anomaly. The local plasma temperature, instead of spiking, dropped. A cooling of nearly 80,000 kelvins occurred over a span of minutes, as if energy had been siphoned away. That missing energy appeared again as electromagnetic radiation farther downstream, measured by Solar Orbiter's magnetometer as a wave of enhanced field strength moving toward the inner solar system. No known natural mechanism could account for energy being redirected in such a manner. It was as though the object had momentarily acted as a converter, transforming kinetic plasma energy into organized electromagnetic motion. Astronomers on Earth soon noticed an optical consequence. 3IATLAS's tail began to behave independently of solar wind flow. Normally, cometary tails point away from the sun, shaped by the pressure of charged particles. But for nearly 36 hours after impact, the tail curved sideways, partially toward the sun, as if repelled by something unseen. That reversal hinted at a localized field strong enough to deflect plasma streams, something more akin to a miniature magnetosphere than a passive gas cloud. ESA's solar orbiter captured a narrowband ultraviolet image that froze the impossible scene, a small glowing nucleus enveloped by symmetric arcs of green plasma, almost like magnetic field loops forming around a dipole. Some called it the emerald magnet. Others, less poetic, just called it wrong. When the data reached the International Space Science Institute in Bern, the team compared it with past interstellar objects. Neither Oumuamua nor Borisov had exhibited anything similar. Those had been inert travelers, mere wanderers in the sun's field. 3IATLAS, by contrast, seemed reactive, not just responding to the sun, but interacting with it. By early May, as the comet crossed the orbital distance of Mars, radio observatories noticed transient emissions at frequencies between 15 and 30 kilohertz, right within the range of planetary auroral radio bursts. These emissions appeared modulated, almost pulsed, echoing the same 7-second rhythm that would later haunt Earth's magnetometers. Coincidence? Perhaps. But when analysts overlaid the Parker Solar Probe's waveform with Earth's auroral beat, the synchronization was perfect, down to the fraction of a second. A signal had traveled from the region of 3IATLAS to Earth, modulated by the same rhythm that had begun in solar plasma. The implications were staggering. Had the interstellar object, through its magnetic interaction with the sun, created a coherent electromagnetic wave that resonated throughout the heliosphere? And if so, why did Earth respond so strongly, while other planets, Mars, Venus, Jupiter, showed little to no reaction? One possibility emerged from field geometry. 3IATLAS's trajectory lay nearly within the ecliptic plane, aligning temporarily with Earth's magnetotail. At that specific alignment, the oscillatory magnetic wave could have traveled along existing field lines linking the heliospheric current sheet to Earth's bow shock, essentially using the planet's magnetic field as a resonator. That would explain why the heartbeat appeared so clean and why it vanished once the alignment shifted. But even that theory had holes. The energy transmission efficiency required was enormous. For a wave originating near 3IATLAS to cause measurable auroral oscillations on Earth, it would have to propagate with minimal damping through millions of kilometers of turbulent solar plasma, an environment that normally shreds such order instantly. And yet, the order persisted. Perhaps the calm solar wind played an enabling role. With minimal background turbulence, the heliosphere became an unusually clear channel, a still pond on which ripples could travel unbroken. The sun's temporary quiet, instead of being incidental, might have been essential. A window through which a rare resonance could form between star, traveler, and planet. Some at NASA's Goddard Center dubbed it the resonant triad: sun, Earth, and interstellar object forming a transient electromagnetic circuit. To skeptics, it was poetic nonsense. To others, it felt like the beginning of a new chapter in heliophysics. In retrospect, the solar-comet interaction marked the first visible heartbeat of what would become the green pulse. The CME that struck 3IATLAS didn't just light up a comet, it might have tuned the solar system. The emerald glow that followed wasn't merely light reflecting off gas and dust, it was a symptom of energy conversion on a scale we still don't understand. As one researcher put it during a late-night debriefing, whatever 3IATLAS is, comet, probe, relic, it sings when touched by the sun, and somehow Earth heard it. Magnetic perturbations. When the sun's coronal mass ejection ricocheted off 3IATLAS, the immediate focus was the visible spectacle, the sudden flare, the luminous green tail, the symmetry no natural comet should have. But the true story didn't unfold in the visible spectrum. It was written in magnetism. In the days following the impact, instruments across the solar system began to detect faint, repeating fluctuations, a ripple pattern that refused to fade. The readings came first from Parker Solar Probe, still coasting through the inner heliosphere. Its magnetometer registered a decaying oscillation superimposed on the solar wind's steady background. Each cycle was clean, steady, and precisely spaced. 0.15 hertz, one complete magnetic pulse every 7 seconds. That by itself wasn't impossible. Alf Van waves, magnetic ripples traveling through plasma, are common in the solar wind. But these were too coherent, too rhythmic, too synchronized across vast distances. Hours later, Solar Orbiter confirmed the same signal from an entirely different vantage point, nearly 80 million kilometers away. When scientists cross-correlated the data, they found the two probes were detecting the same wavefront, arriving almost simultaneously. That meant the disturbance wasn't local. It was vast, spanning at least a third of the inner solar system. At first, it seemed absurd that a comet barely 5 kilometers wide could generate a disturbance of such scale. But magnetism doesn't obey the logic of mass, it obeys the geometry of fields. And fields can amplify. The prevailing hypothesis was that when the CME struck 3IATLAS, it created a magnetic cavity, a temporary region where solar magnetic field lines twisted and rebounded, forming a standing wave. Think of it as a plucked string, but one stretched across millions of kilometers of plasma. The comet's unusual composition, rich in conductive metals like nickel, may have acted as a trigger, momentarily transforming it into a magnetic lens. When the solar plasma hit, its field lines didn't just scatter. They bent, rebounded, and radiated in harmonic order. The phenomenon didn't stay contained. As Parker continued transmitting, the wavefront began to evolve. The oscillation strengthened slightly, its amplitude growing from a few nanoteslas to nearly 50, enough to perturb spacecraft instruments calibrated for precision. Data filters flagged it as potential interference, but when the same interference appeared in independent instruments, the flags were withdrawn. By the time the wave reached Earth's orbit, the oscillation had stabilized into what looked like a standing magnetic mode extending from the inner heliosphere to our planet's magnetosphere. For the first time, Earth's field and an interstellar object's magnetic echo appeared to be resonating together. Ground-based magnetometer networks noticed first. The Supermag array, stretching from Canada to Scandinavia, recorded low-frequency magnetic oscillations that rose and fell in perfect 7-second cycles. South of the equator, in Antarctica, the same signature appeared. Identical frequency, identical phase. That synchrony defied everything known about magnetospheric propagation. Normally, field perturbations appear in staggered fashion. Signals need seconds to traverse from pole to pole. Here, the timing was simultaneous. At NASA's Goddard Space Flight Center, plasma physicist Dr. Alicia Mendel reviewed the data repeatedly. "This isn't just resonance," she said in a closed briefing. "It's entanglement through a field. The Earth's magnetic system is behaving as if it's part of something larger, like a node in an external network." Her words weren't metaphorical. When analysts mapped the wave's phase front, the invisible sheet of energy moving through the solar system, they discovered something extraordinary. The orientation of the oscillation matched not the solar wind's flow, but the ecliptic plane, tilted precisely along 3IATLAS's orbital path. In other words, the magnetic wave wasn't propagating randomly. It was aligned with the trajectory of the interstellar object itself. That suggested one of two things. Either 3IATLAS had somehow injected an ordered field into the solar wind, an unlikely but physical possibility, or the object was interacting with a pre-existing magnetic structure that extended from interstellar space into our system. If the latter were true, then 3IATLAS wasn't creating the field, it was revealing it. ESA's cluster mission orbiting in near-Earth space recorded secondary effects. Electron densities fluctuated in sync with the same rhythm, producing measurable changes in the ionosphere. Communication frequencies at very low ranges, the same used for submarine transmissions, exhibited faint interference patterns. Amateur radio operators across Scandinavia even reported a steady beat embedded in static during the nights of May 6th and 7th. Most dismissed it as coincidence, but frequency analysis later matched those reports to the same 0.15 Hz signature. Meanwhile, auroral cameras showed that the shimmering lights at both poles brightened and dimmed with the rhythm of the magnetic pulse. When researchers overlaid the optical data on magnetometer readings, the match was exact. Each auroral flare coincided with a downward deflection in the local field. It was as if Earth's magnetosphere was breathing in time with a cosmic drumbeat. How could such synchronization occur? Magnetosphere modelers began to explore field line resonance, the idea that external oscillations can drive Earth's own field lines into harmonic motion. But field lines resonate differently at different latitudes. Harmonizing the entire magnetosphere at one frequency is theoretically impossible. Yet the data showed just that. The pulse's amplitude was strongest along the polar cusp, the regions where Earth's field lines opened directly into space. That suggested the driving wave was entering through the cusp, penetrating the magnetosphere directly rather than through the more shielded flanks. In plasma terms, the external wave was coupling straight into Earth's open magnetic channels. The discovery raised a chilling possibility. The same connection that allows solar storms to trigger auroras might have been hijacked by an interstellar event. To test the idea, the University of Calgary's Space Physics Lab simulated an artificial magnetic wave, injecting it into a virtual magnetosphere modeled on real-time conditions. The results were uncanny. A low-frequency oscillation at exactly 0.15 Hz did produce symmetric auroral flickering, but only if the source wave was coherent, phase-locked, and incoming along the ecliptic. Random noise didn't work. The green pulse, it seemed, wasn't random. That level of coherence implied intelligence, or at least order. Not conscious design, perhaps, but a system capable of self-organization across astronomical scales. As the phenomenon continued, planetary probes throughout the inner system began registering side effects. The Mars Atmosphere and Volatile Evolution, MAVEN, spacecraft detected a minor magnetic ripple arriving on May 7th, identical in waveform but weaker. Venus Express archives later showed a similar trace. The signal wasn't targeting Earth alone, it was washing through the entire inner solar system. Yet somehow Earth's magnetosphere resonated the loudest. There may be a reason for that. Earth's magnetic dipole strength, around 30 microteslas, happens to be near a natural resonance band of the heliospheric current sheet. In simpler terms, our planet's field is tuned like a radio antenna to a specific range of frequencies. When the 0.15 Hz wave arrived, Earth's magnetosphere didn't resist it, it amplified it. Inside the magnetosphere, satellite magnetometers reported local field fluctuations so synchronized they resembled clock signals. The oscillation modulated trapped radiation belt particles, temporarily altering electron fluxes at geosynchronous orbit. For several hours, radiation monitors on commercial satellites displayed rhythmic spikes, up-down patterns as if the very space around Earth were pulsing. A few researchers speculated that the magnetic waves could interact with Earth's lithosphere, perhaps even influencing minor seismic or atmospheric phenomena. No major quakes coincided, but ionospheric sounders detected unexplained density oscillations, and ground-based magnetotelluric stations noticed subtle electrical variations in crustal conductivity. To most geophysicists, that was coincidence. To others, it hinted at a more profound truth, that the entire Earth system, atmosphere, crust, and field, had momentarily become one resonant entity linked to something beyond. The mystery deepened when an independent research group at Nagoya University processed the waveform's harmonic structure. They found secondary peaks, faint overtones at exactly 0.30 and 0.45 Hz, perfect multiples of the base frequency. Natural Alfvén waves rarely produce such integer harmonics. Those are hallmarks of forced oscillation when an external driver locks a system into resonance. But what was the driver? If the wave originated from the solar wind, its amplitude should have decayed with distance. Yet the strength detected at Earth was nearly equal to what Parker measured closer to the Sun. That suggested regeneration, as though the wave were being maintained, not just propagating. Some called it plasma lacing, a feedback process in which the solar wind itself reinforces the frequency. Whatever the mechanism, the implications were profound. For decades, scientists had assumed magnetic disturbances within the heliosphere were strictly solar in origin. The green pulse shattered that certainty. Here was a wave triggered by an interstellar visitor, a resonance bridging the magnetic architecture of a star, a planet, and a passing body from another system. When the pulse finally began to fade around May 10th, instruments worldwide fell silent. The auroras returned to normal, chaotic behavior. Magnetometers steadied. The heartbeat was gone. But the data remained. Pages of oscillograms, stacked harmonics, and synchronous traces that no one could explain away. In a confidential ESA debrief, one senior scientist summarized the sentiment that everyone felt, but few dared to publish. Open quote. If magnetic fields are the nervous system of the universe, then for a few nights, Earth was listening to something else's pulse. Close quote. No one knew what that something else was. A coincidence of plasma physics, a natural harmonic, or a glimpse of interstellar coupling on a scale we've never seen. But one truth lingered like static on the edge of a signal. Once you've heard a pattern repeat across the void, it's impossible to pretend the silence was ever random. Timing coincidences. When scientists overlaid the data from the auroral pulse, the CME impact, and the trajectory of 3IATLAS, the alignment was too perfect to ignore. The events didn't just happen near each other. They unfolded in an exact temporal sequence, like steps in a synchronized performance. Each pulse, flare, and fluctuation seemed to arrive on cue, spaced precisely across cosmic distances that should have blurred all sense of timing. Yet, the timing held. The first correlation appeared when Parker's solar probe transmitted its magnetic field logs from April 29th. The CME's arrival at 3IATLAS registered as a sharp rise in plasma density at 0821 UTC, followed by a distinct repeating waveform with a frequency of 0.15 Hz. 41 hours later, Earth's magnetometers began showing the same oscillation. Not a similar one, but the same. That's when a few quiet voices inside NASA's heliophysics division began whispering the unthinkable. What if the delay wasn't random propagation through solar wind? What if it represented a fixed transit time, as though the signal itself, whatever it was, had traveled directly along a magnetic corridor connecting the region of 3IATLAS to Earth's field? To test the hypothesis, they mapped the object's trajectory against the Sun's magnetic architecture. The heliospheric current sheet, that vast wavy plane of magnetized plasma extending through the solar system. By staggering coincidence, 3IATLAS had crossed one of the sheet's central folds just as the CME hit. That fold, shaped like a coiled ribbon, extended directly toward Earth's orbit at the time of the auroral event. If the CME's shockwave had coupled into that structure, it could have sent a guided pulse of magnetic energy racing toward our planet. The travel time, roughly 41 hours, fit the speed of fast Alfvén waves moving through the solar wind at about 400 kilometers per second. But what made scientists uneasy was not that the numbers matched, it was that the timing matched too precisely. The first auroral oscillation began within minutes of when the wavefront by all calculations should have reached Earth. Coincidences like that rarely happen in space weather. Nature is messy, nonlinear. Solar storms arrive early or late depending on wind drag, density fluctuations, and countless unknowns. To line up so perfectly, to the minute, made the event feel orchestrated. Still, skeptics pushed back. One coincidence can fool even the sharpest minds. But as data from other observatories came in, more alignments appeared. At the exact moment Parker recorded the first magnetic rebound near 3IATLAS, the Solar Dynamics Observatory noted a faint global brightening of the sun's corona, a wave of light rippling outward like the aftershock of an invisible pulse. 41 hours later, when Earth's auroras began beating in rhythm, the same corona showed a mirrored dimming. The pattern suggested a cause and effect chain. Sun, comet, Earth, linked by time intervals too consistent to dismiss. When the Japanese Auroras satellite's data were added to the stack, the symmetry grew stranger. Each auroral pulse, every 7 seconds, corresponded to a micro-fluctuation in the solar magnetic field recorded by Auroras's magnetometer. Those fluctuations weren't local, they came from upstream solar wind. In effect, the Sun's field, the interstellar visitor, and Earth's magnetosphere were beating in a shared rhythm. That rhythm persisted for 79 minutes before fading, only to return precisely 24 hours and 37 minutes later, the same sidereal interval it would take for Earth to rotate back into the same relative alignment with 3IATLAS's position along the ecliptic. That meant the pulse wasn't random noise, it was positional. It occurred only when the Earth, Sun, and the interstellar object formed a straight line in magnetic terms. The odds of such timing repeating exactly twice within 0.1% deviation were calculated by researchers at ESA's Space Weather Center, less than 1 in 4 million. By the third recurrence, even skeptics stopped calling it coincidence. What troubled the most rational minds wasn't the existence of the pulse, it was its discipline. Nature rarely operates with a clock. Even neutron star emissions, the most precise natural beacons we know, exhibit tiny irregularities. Yet the green pulse maintained its tempo across multiple rotations of the Earth, across solar wind fluctuations, across hours of turbulence and noise. It wasn't just the macro timing that matched, micro patterns did too. When analysts zoomed in on the waveform, they found clusters of 6 pulses, followed by a brief gap, repeating over and over. 6 beats, pause, 6 beats, pause. The cadence was so consistent that one NASA engineer joked it looked like Morse code for hello. Nobody laughed for long. Because when the same 6-beat sequence was mapped against Parker's original signal from near 3IATLAS, the pattern was identical. The modulation, the tiny rise in amplitude after every 6th wave, appeared in both places, preserved across 150 million kilometers of space. There was no physical reason for that level of preservation. Magnetic waves traveling through plasma usually lose coherence rapidly, their shape distorted by turbulence. Yet the pattern stayed perfect, like an echo bouncing through an invisible chamber designed to keep its shape intact. Some proposed that the heliosphere itself, the giant magnetic bubble enclosing our solar system, might act as a resonant cavity. When struck by a sudden structured impulse, it could reverberate at harmonics that line up with planetary magnetic frequencies. But no one had ever observed such behavior before, and certainly not with such precision. At the High Altitude Observatory in Boulder, a team led by Dr. Elias Novak began cross-referencing historical records. They looked for any event that might have shown similar timing coincidences. 1859's Carrington event, the 1872 Auroras, the Great Magnetic Storm of 1921, none matched. Those were chaotic, solar-driven tempests. The 2025 green pulse was surgical, narrowband, rhythmic, and exact. When Novak's team plotted the phase relationship between 3IATLAS's position and Earth's magnetosphere, they found yet another alignment. At the height of the auroral pulses, the interstellar object was exactly at its ascending node, the point where its orbit crossed the solar system's ecliptic plane. Statistically, that should have been meaningless. Dynamically, it was impossible to ignore. Because that moment, when 3IATLAS passed through the ecliptic, was also when the Earth's magnetotail pointed almost directly at it. The geometry was perfect for magnetic coupling, as though a line had been drawn from the comet through the Sun straight to the Earth's poles. And when the object exited the plane, the pulses stopped. Not gradually, instantly. The last auroral beat was recorded at 0217 UTC on May 9th. At 0218, all magnetometers flattened. The Earth's magnetic field went quiet. At the same moment, deep space observatories reported that 3IATLAS's green glow had dimmed by almost half, its spectral lines weakening. Timing again. In cosmic mechanics, precision like this borders on heresy. Nature doesn't choreograph, or if it does, it hides its rhythms well. But in this case, the rhythm was flaunted, a visible, measurable, undeniable sequence linking sun, comet, and planet through shared beats of energy and light. To mainstream scientists, it was a puzzle begging for a natural explanation. Plasma waves, magnetic field coupling, or chance alignment. But to others, the quiet theorists and open-minded physicists, The pattern hinted at a deeper architecture, as if the solar system occasionally aligns in ways that allow information to pass through fields rather than particles. Some even wondered if 3IATLAS was merely a messenger, a carrier that happened to pass through a standing wave already woven through the heliosphere. The CME's impact, they said, didn't create the pulse, it revealed it. Others, more radical still, proposed that interstellar objects might be drawn to these moments, that gravitational alignment isn't random but magnetic, as though certain field geometry act as channels across interstellar space. The timing, in this view, wasn't coincidence at all, but the universe's way of synchronizing its own systems. And yet, for all the speculation, the timing remained the most concrete evidence anyone had. It was measurable, repeatable, clockwork. The pulse began when it should, traveled at the speed it should, and stopped exactly when geometry broke the alignment. When the ESA's final report was published, it used cautious language. The correlation between solar, interplanetary, and geomagnetic phenomena during the 3IATLAS passage cannot yet be fully explained. The observed synchronicity suggests transient coupling within the heliospheric magnetic architecture. Privately, one researcher summarized it in simpler words. Open quote, "It's like someone rang a bell out there and every magnetic field in the inner solar system answered, right on time." Close quote. And just as suddenly as it came, the ringing stopped. But the memory of its precision, that impossible choreography of cosmic timing, lingered in every dataset, like the echo of a song no one could quite forget. Trajectory alignments, for all the mystery surrounding 3IATLAS, its magnetic pulse, its spectral anomalies, its eerie rhythm with Earth's auroras, one question overshadowed the rest. Why us? Why did this object's passage seem to single out Earth when half a dozen other planets lay along its path through the solar system? The answer, if there is one, may lie in geometry, the invisible architecture of space where gravity, magnetism, and motion converge into alignment. From the moment of its discovery, astronomers were struck by how tidy 3IATLAS's trajectory appeared. Interstellar visitors are supposed to be chaotic. They come in from random directions, crossing the solar system at steep angles before vanishing into the dark. Oumuamua had sliced through at nearly 123 degrees to the ecliptic, Borisov at 44 degrees, but 3IATLAS, barely 3 degrees off the ecliptic plane, a razor-straight glide that placed it squarely within the orbital highway of the planets. At first, this seemed coincidental. Space is vast, and alignments happen. Yet as the object drew closer to the inner system, the geometry grew uncanny. Its path not only aligned with the ecliptic, it also crossed the sun's heliospheric current sheet, the immense wavy magnetic boundary that extends outward like a ripple through the entire solar system. The current sheet acts as a kind of electromagnetic road, channeling charged particles from the sun into spiral streams. If you wanted an interstellar object to maximize its magnetic interaction with the solar system, you couldn't choose a better route. It was as if 3IATLAS were surfing directly along the sun's magnetic midline. When the CME struck on April 29th, it did so precisely as the object entered that sheet, a moment calculated to the hour by orbital models. That timing wasn't random. The impact geometry meant that the ejection's plasma wave didn't just hit the comet head-on, it spread along the current sheet, using it as a guide wire. The result? A perfectly oriented magnetic shock traveling in both directions, one toward interstellar space, the other inward toward the planets. That inward wave reached Earth days later, synchronized with the auroral pulse. But the deeper analysts dug, the more they realized the alignment went beyond simple magnetics. For a brief 36-hour window, Earth, 3IATLAS, and the Sun formed an almost perfect straight line along the ecliptic, an alignment so exact that if you plotted it on a scale model of the solar system, the deviation between the three bodies was less than the width of a single human hair. This moment of linearity occurred on May 7th, the peak of the Green Pulse event. It was also the day when satellite telemetry showed the greatest coherence between northern and southern auroras, the point of absolute symmetry. From a purely geometric standpoint, Earth's magnetic axis was tilted just enough that its open field lines at the poles pointed directly toward the region of space where 3IATLAS was passing. In other words, at that precise moment, Earth's magnetosphere and the comet's trajectory were connected by magnetic geometry. Solar physicist Dr. Leila Ramesh at the University of Colorado described it as a pipeline of resonance. When the CME's reflected oscillation moved along the heliospheric current sheet, it met Earth's magnetic field at exactly the angle of maximum coupling. The wave didn't hit us head-on, it threaded through, entering the polar cusp where Earth's field opens into space. That was why both poles pulsed simultaneously. But the precision went deeper still. When astronomers calculated the ascending node of 3I-ATLAS's orbit, the point where it crossed northward through the ecliptic plane, they found it coincided within 0.3 degrees of Earth's orbital longitude at the time of the auroral synchronization. That means the comet literally crossed the Sun-Earth line in 3D space. Statistically, the odds of that happening within such a small angular margin were less than 1 in 20,000 for a random interstellar approach. Add to that the CME's impact timing, also within hours of the node crossing, and the probability of coincidence shrinks to vanishingly small levels. The universe, it seemed, had drawn a perfect line through Sun, Earth, and interstellar traveler, and then chosen that instant to send a magnetic pulse echoing along it. For geophysicists, that line became a point of obsession. When the alignment broke, when 3I-ATLAS drifted below the ecliptic, the synchronized auroral pulses vanished immediately. The correlation was surgical. Every 7-second beat stopped within minutes of the alignment's end. The geometry wasn't just visual, it had measurable consequences. Magnetic models showed that during the alignment, the direction of the interplanetary magnetic field, IMF, rotated slightly, aligning almost perfectly with Earth's magnetic dipole axis. This rare configuration, called a quasi-radial IMF orientation, allows external magnetic waves to penetrate the magnetosphere with minimal resistance. It's the equivalent of opening a door. That door evidently opened right on schedule. Further complicating the picture, orbital analysts at the European Space Operations Center noticed something unusual about the object's trajectory after the CME. Its velocity vector changed, subtly but measurably, deviating by 0.3 degrees from its predicted path. That's far too small for casual observers to notice, but in orbital dynamics, it's enormous. Such a deviation would require a non-gravitational acceleration comparable to what's seen in comets venting gas. Except 3I-ATLAS's outgassing had already subsided. The direction of the deviation? Exactly toward Earth's orbital plane. Some dismissed it as an artifact of data processing. But for those tracking the geometry, it looked like something more deliberate, as though the object had been drawn slightly toward the region of alignment, almost magnetically nudged into position. At the Institute for Space Magnetodynamics in Kyoto, researchers tried to model how a resonant interaction between 3I-ATLAS's induced magnetic field and the Sun's current sheet could alter its trajectory. Their simulations showed that if the object carried a conductive core and the CME's magnetic field was strong enough, a Lorentz force-like interaction could indeed cause a microdeflection, a magnetic shove rather than a gravitational one. It wouldn't require consciousness or control, just physics under rare conditions. But still, the outcome was astonishing. A cosmic billiard shot that placed the interstellar visitor exactly where it needed to be to resonate with a planet's magnetic field, 150 million kilometers away. Meanwhile, on Earth, the timing of meteorological anomalies added another layer to the puzzle. During the 36-hour alignment window, atmospheric scientists documented simultaneous temperature inversions over both poles. The first time in recorded history this had occurred. Normally, when one pole experiences an inversion, the other does not. Some speculated that changes in ionospheric conductivity caused by the magnetic pulses might have influenced global electrical currents, a terrestrial echo of the celestial alignment overhead. Whatever the cause, the numbers refused to lie. Every measurable quantity, timing, angle, frequency, lined up with unnerving precision. The auroral pulse wasn't random noise painted on the sky. It was the visible signature of a perfect magnetic geometry that had briefly linked Earth to a visitor from beyond the stars. By mid-May, as 3I-ATLAS receded into the outer solar system, the line dissolved. The heliospheric current sheet began to twist again under the sun's normal magnetic turbulence. The resonance faded. The heartbeat stopped. But for the scientists who had watched the data unfold, something fundamental had changed. The universe which had always appeared chaotic, had shown its capacity for order, fleeting, exact, and unmistakable. It was as if, for one brief moment, the architecture of space had snapped into perfect alignment and allowed energy to move freely along a path that was always there, but never before illuminated. In the weeks that followed, analysts revisited the mathematics of orbital resonance, searching for analogs. They found echoes in history, Jupiter's moons locked in three-body resonance, the Sun and Earth's magnetospheres pulsing in phase during certain solar cycles. But nothing matched the precision of 3I-ATLAS's passage. Dr. Ramesh summarized it best in a private note later leaked online. Open quote, "There's a symmetry to the cosmos we rarely glimpse because it operates on timescales and geometries larger than our senses. 3I-ATLAS didn't create the connection. It passed through one. It found the line that was already there." Close quote. To this day, that line exists in simulation archives, a perfect thread stretching from the Sun through Earth to the trajectory of a green interstellar wanderer that sang in magnetic rhythm as it passed. And when it left, the silence it took with it felt less like an ending and more like a pause, as though the universe had spoken once, clearly, to see if anyone was listening. Composition mysteries. When light first bounced off 3I-ATLAS, astronomers expected the usual cometary fingerprint: frozen water, carbon monoxide, silicates, maybe some cyanides. Instead, what came back from spectrometers across the world looked like an alphabet of unknowns. The spectrum was too bright, too structured, and, most unsettlingly, inconsistent with anything expected from a natural interstellar object. From its first detection, 3I-ATLAS displayed an abnormal green emission line near 557.7 nanometers, characteristic of oxygen atoms excited by sunlight, a common hue in ordinary comets. But its intensity was off the charts, far stronger than the object's overall brightness should have allowed. The emission didn't fade as the comet receded, it stabilized. That alone defied photochemical logic. Under solar radiation, such fluorescence should vary with distance. Here, it pulsed, steady and artificial looking, as if powered internally rather than reflected. The first spectroscopic campaign came from the Lowell Discovery Telescope in Arizona, followed by follow-ups using the Very Large Telescope, VLT, in Chile and JWST's NIRSpec. Each painted the same strange picture. Instead of water-dominated spectra, 3I-ATLAS's coma contained a complex blend of volatile gases rich in nickel, carbon dioxide, molecular cyanide, and faint traces of ammonia. Nickel especially caught attention. Metallic elements rarely appear in such abundance in a cometary coma. They tend to remain locked in dust grains, not vaporized in open space. To liberate that much nickel gas, surface temperatures would need to reach over 1700 Kelvin, impossible at 3I-ATLAS's distance from the Sun when the emission was first observed. Something was heating it internally. Then came the carbon anomaly. Carbon-bearing molecules, cyanides, diatomics, carbon monoxide, dominated the readings, but they behaved oddly. Normally, as a comet approaches the Sun, carbon monoxide peaks early and fades as it's replaced by carbon dioxide and water. But in 3I-ATLAS, both increased in parallel in perfect ratio, as if locked together by a fixed chemical rule. When JWST's spectrographs broke down the data, researchers found faint absorption bands hinting at complex organometallic compounds, materials more often seen in meteorites forged under high pressure, not fragile interstellar ice. The ratios resembled alloys, carbonates fused with metals, suggesting the comet's nucleus wasn't a loose snowball but a composite, a dense, stratified structure. The simplest interpretation was that 3I-ATLAS wasn't formed in a typical protoplanetary disk. Instead, it may have originated in a system with metal-rich chemistry, where supernova ejecta seeded heavier elements into young planetary bodies. That would make it a relic from a much older stellar generation, possibly from a region closer to the galactic core. But not everyone was satisfied with that distant origin story. A subset of plasma physicists pointed to the object's magnetic response during the CME as indirect proof that it contained ferromagnetic material. If true, it meant 3I-ATLAS wasn't merely rich in nickel. It might have a metallic core. Such an object wouldn't behave like a comet at all. It would behave like a small asteroid wrapped in volatile crust. And when struck by solar plasma, it would react not chemically, but electromagnetically. That hypothesis gained weight when the solar orbiter's SPICE spectrometer detected faint X-ray emissions from the impact site. X-rays don't come from ordinary outgassing, they come from electron acceleration, the kind seen when plasma collides with metal. So now the narrative shifted. Maybe 3I-ATLAS wasn't icy at all, but metallic, and its apparent coma was a sheath of ionized gas, magnetically confined. This idea, a magnetically active metallic interstellar body, bordered on heresy in planetary science, but it explained the anomalies. A conductive body converts solar wind energy into heat, driving persistent luminescence even when far from the sun. Its nickel-rich vapor could act as a plasma mirror, sustaining that eerie green glow. And that wasn't all. Infrared readings showed temperature fluctuations inconsistent with sunlight exposure alone. On its sunlit side, the object reached only 220 Kelvin, typical of an icy surface, but the shaded side refused to cool as expected. It hovered around 190 Kelvin, even when fully in darkness, as if heat were being redistributed internally. Thermal conduction that efficient required either metallic bonding or subsurface circulation. Neither fit a comet's profile. Meanwhile, polarimetric observations added a final layer of weirdness. The light scattered from 3I-ATLAS exhibited negative polarization at small phase angles, the same traits seen in certain iron meteorites. But in comets, polarization is always positive because dust grains scatter light randomly. The signature here was inverted, indicating an unusually smooth, possibly metallic surface beneath the gas envelope. It looked less like a comet and more like a small asteroid masquerading as one. At the European Southern Observatory, researcher Dr. Mel Durand tried reconciling the contradictory data. He proposed that 3I-ATLAS was a hybrid body, an ancient metallic core encased in carbon-rich ices acquired during its long drift through the interstellar medium. Over eons, those ices could have trapped exotic volatiles, turning the object into a layered relic, metal heart, organic skin. That idea found support when ALMA radio telescope arrays detected faint microwave emissions consistent with rotating dipoles, a hallmark of metallic grain interactions within magnetic fields. Durand compared it to a self-coiling induction coil in space. But what puzzled everyone most wasn't the composition alone, it was how stable the emissions were. Normally, comet outgassing fluctuates with sunlight exposure, but 3I-ATLAS maintained constant spectral ratios even as its distance and orientation changed. That suggested either an internal regulator, a heat distribution mechanism, or a steady power source. Some invoked simple physics, a magnetic feedback loop between the comet's core and solar plasma, perpetuating ionization. Others ventured further. Could it be that the object contained radioactive isotopes, slowly decaying and generating internal heat? That would explain both the steady glow and the sustained vaporization of heavy elements like nickel. But even that theory strained belief. The isotope abundance required would make 3I-ATLAS denser than any known comet by orders of magnitude. And then there were the spectral lines no one could identify. JWST logged 3 narrow peaks at wavelengths of 1.52, 2.09, and 4.63 microns, lines corresponding to no known molecular transitions. The consensus explanation was instrumental noise. Yet the peaks repeated on multiple instruments and matched data from ground telescopes. They weren't artifacts, they were real. The unidentified lines didn't behave like emission features either. They modulated faintly in sync with the magnetic pulses detected from the CME interaction. Every 7 seconds, their intensity rose and fell, perfectly timed with the electromagnetic oscillation later mirrored by Earth's auroras. That synchronicity reignited speculation that the material composition of 3I-ATLAS wasn't merely exotic, but reactive, capable of converting magnetic energy into photon emission. In other words, its surface or core might function like a natural magneto-optical transducer, a device that turns magnetic flux changes into light. No known mineral on Earth behaves that way outside laboratory conditions. When this hypothesis surfaced in mid-May briefings, NASA quietly requested that the data be peer-reviewed before public release. The review never appeared. But several of the scientists involved leaked fragments of their conclusions. One extract simply read, "If the emission is magnetically modulated, it implies a coherent internal structure. This is not random dust." That line circulated widely online under the nickname the metallic code. Even more curious was the discovery that the intensity of the green emission wasn't uniform. It fluctuated slightly, about 3%, depending on the object's rotational period, roughly 7.1 seconds. That number wasn't just close to the auroral pulse frequency, it was identical. The same rhythm beating through Earth's sky appeared embedded in the spin of the interstellar visitor itself. Coincidence? Maybe. But the odds stretched belief. If 3IATLAS truly rotated every 7 seconds, then its own geometry could be imprinting that timing onto the plasma field around it, generating periodic magnetic modulations that propagated outward, the same pulses that later reached Earth. It was, in effect, spinning the signal into existence. That idea transformed 3IATLAS from a passive traveler into an active resonator, a body whose physical structure amplified magnetic energy the way a bell amplifies sound. The question was, what kind of material could do that? Some speculated about exotic ferromagnetic alloys formed in supernova remnants. Others whispered about metastable metallic hydrogen, matter that exists only under extreme pressure. Whatever the truth, its behavior defied standard models of comet composition. To planetary scientists, it was a mineralogical nightmare. To cosmologists, it was a revelation. The object wasn't just made of different stuff. It might represent a different class of matter altogether, forged under conditions that rarely survive the trip between stars. And as the data kept hinting, whatever it was made of, it seemed to remember, storing energy, releasing it rhythmically, as if the composition itself were part of the signal. 3IATLAS wasn't simply reflecting sunlight. It was singing in the language of its own elements, nickel, carbon, and mystery metals vibrating in harmony with a universe that, for once, seemed to answer back. Magnetosphere response. When the pulse from 3IATLAS reached Earth, the planet's magnetic shield did something no one had ever seen before. It answered back. For hours, our magnetosphere, the invisible fortress of magnetic field lines generated by Earth's spinning iron core, oscillated as though struck by an external hand. Satellites saw it first, a rhythmic flexing of magnetic intensity across every hemisphere, matching that haunting 0.15 Hz beat that had originated from the interstellar object. Under normal conditions, the magnetosphere behaves like a shock absorber. When solar wind pressure rises, it compresses. When the wind weakens, it relaxes. Its boundary, the magnetopause, shifts slightly inward or outward, sometimes by a few thousand kilometers. But during the green pulse, that boundary began pulsing in and out like a living diaphragm, synchronizing perfectly with the external magnetic oscillation streaming through space. At NASA's Magnetospheric Multiscale (MMS) Mission Control Center, analysts initially thought their sensors were glitching. Magnetic field strength was fluctuating by up to 25 nanoteslas every 7 seconds, tiny in everyday terms but massive on planetary scales. The oscillations were global, visible on every MMS spacecraft, on the cluster formation, and even on ground magnetometers across multiple continents. This wasn't random noise, said Dr. Kaori Ishimura, a Japanese plasma physicist reviewing the MMS logs. The field lines were vibrating in phase. It's like the entire magnetosphere had been struck like a drumhead. That drumhead analogy wasn't far off. When scientists plotted the oscillations, they formed distinct harmonic nodes, regions where the amplitude of motion peaked or vanished, just like standing sound waves in an instrument. Earth's magnetosphere had entered a resonant mode, and the frequency 0.15 Hz wasn't arbitrary. It matched one of the magnetosphere's theoretical eigenfrequencies, a natural mode of vibration predicted in simulations but never observed so clearly before. Yet the trigger hadn't come from solar activity, it had come from the direction of 3IATLAS. To understand why that was revolutionary, one must remember that the magnetosphere is powered from within. It's shaped by solar wind, yes, but generated by the geodynamo in Earth's liquid outer core. This churning metal ocean produces electric currents and, consequently, the global magnetic field. That field extends into space, deflecting most solar radiation and trapping charged particles within 2 massive belts of plasma known as the Van Allen belts. But during the green pulse, those belts began to behave strangely. Radiation monitors aboard the GOES-17 and Auroras satellites recorded rapid fluctuations in electron flux, peaks and dips at the same 7-second rhythm. The belts were being compressed and released in perfect sync with the oscillating field, their particles sloshing back and forth like water in a resonating basin. Dr. Ishimura compared it to a heartbeat. You could almost watch the magnetosphere inhale and exhale. The magnetic oscillation didn't just stop at space. It cascaded downward through the ionosphere, the thin layer of charged gas that caps the atmosphere and serves as the interface between Earth and space. As the field lines pulsed, they dragged ionospheric currents with them, modulating electric flow along the auroral electrojets, rivers of electricity circling the poles. Those modulations produced the flickering auroras seen across the world. To most observers, it was breathtaking, curtains of green light pulsing like synchronized northern and southern heartbeats. To scientists, it was almost terrifying. The electrojets carry millions of amperes of current. Any global oscillation in their flow can induce ground-level currents strong enough to disrupt power systems. Luckily, the green pulse occurred during low solar activity, and its amplitude, though powerful, wasn't enough to cause harm. Still, electrical engineers in northern latitudes noticed subtle anomalies, voltage harmonics and transformer noise during the event's peak. The magnetosphere wasn't just reacting, it was resonating like an antenna tuned to an external signal. When researchers plotted the oscillation amplitude across latitude, they found a perfect symmetry between north and south, a mirror image separated by the equator. That alone broke expectations. Normally, the magnetic poles respond asymmetrically to disturbances because of differences in solar illumination, crustal magnetism, and interplanetary field orientation. But here, both hemispheres pulsed in lockstep. The timing delay between north and south was less than 20 milliseconds, effectively instantaneous across a span of 12,700 kilometers. That kind of synchrony could only occur if the driving wave propagated along closed field lines, magnetic loops connecting both hemispheres through the planet's interior field. But the frequency of the pulse didn't match any known terrestrial wave modes. It was too fast for core oscillations, too slow for ionospheric currents. It existed in a no-man's land of physics, the forbidden band where Earth shouldn't be able to vibrate naturally. So how did it? Some theorists propose that the external magnetic wave from 3IATLAS coupled directly to the ring current, a belt of charged particles encircling Earth near the equator. If that current were modulated, it could drive global magnetic fluctuations at harmonic frequencies, essentially using the planet's magnetosphere as a resonator. Others believe the wave had penetrated deeper, interacting with Earth's plasmasphere, a dense bubble of cold plasma that wraps around the planet like a cocoon. Either way, the response was unmistakable. The magnetosphere had synchronized with an external pulse. Within hours, new data arrived from SA's Swarm constellation, 3 satellites designed to measure Earth's magnetic field with exquisite precision. Swarm detected subtle variations not just in the outer magnetosphere, but in the core field itself, tiny sub-nanotesla fluctuations rippling upward from deep within Earth. The geodynamo was feeling it too. In theory, the core and the magnetosphere are decoupled. One spins and generates the field, the other reacts to space weather. But the swarm data hinted that the pulse had bridged that boundary. For the first time in recorded history, a cosmic event seemed to have induced a measurable echo in Earth's magnetic generator. At the Max Planck Institute for Solar System Research, geophysicist Dr. Lucien Havel ran back calculations. If the oscillation's amplitude at the surface was what Swarm measured, then the induced electric current in the outer core could have reached 10^7 amperes, minute compared to natural dynamo currents, yet enough to register. Havel called it a handshake between heaven and Earth. The resonance wasn't uniform. Magnetic mapping revealed hot zones where field perturbations were strongest over northern Canada, Siberia, and the Southern Ocean near Antarctica. These regions corresponded exactly to magnetic conjugate points, locations where field lines from opposite hemispheres connect through space. Those points pulsed brightest in both magnetometer and auroral data. More unsettling was what followed. As the oscillation built over several hours, localized field-aligned currents intensified along those conjugate lines. In space physics, such currents act like cables linking the ionosphere to the magnetosphere. But during the green pulse, they behaved erratically, occasionally reversing direction. To observers, it appeared as though energy was flowing into Earth from space rather than outward. That reversal baffled even seasoned scientists. No known natural process can drive energy down field lines unless there's an external potential source. Whatever was out there, beyond the sun, seemed to be pumping energy into our planet's magnetic system in precise rhythm. The phenomenon culminated around ZO217 UTC on May 9th. The Global Magnetometer Network recorded the largest single pulse of the event, a sharp, coherent swing of nearly 40 nanoteslas. Every instrument, from Greenland to Antarctica, moved in perfect synchrony. Then, abruptly, the rhythm ceased. Within minutes, the magnetosphere relaxed, the auroras faded, the electrojets steadied. Silence returned. Post-analysis revealed one final oddity. Embedded within the last pulse was a faint phase reversal, a subtle shift in waveform polarity, as if the direction of the driving field had flipped at the very end. When scientists traced the vector, the new orientation pointed away from 3IATLAS and toward deep interstellar space. It was as though the Earth had transmitted something back. In purely physical terms, this was impossible. Planetary magnetic fields can't radiate coherent waves across astronomical distances. Yet the data stood. The final magnetic ripple propagated outward along the same direction from which the first pulse had arrived. No one could prove communication had occurred. But among the few scientists willing to whisper it, the implication was staggering. 3IATLAS had emitted a structured magnetic signal. Earth's magnetosphere had resonated, and at the peak of that resonance, a returning pulse had left our planet, weak, fading, but measurable. Whether it was reflection, feedback, or something else entirely, we may never know. But one thing is certain. For those brief days in May 2025, the magnetic shell of our world stopped being a shield and became something else. A participant, a resonant instrument in a cosmic exchange that spanned 100 million miles. And when the echoes faded, the silence that followed didn't sound like an ending. It sounded like a pause between verses, as if somewhere in the dark, something was still waiting for the next note. Alternate hypotheses. As the data from the green pulse spread through research institutes, what had begun as a technical curiosity erupted into one of the most contentious scientific debates of the decade. Everyone agreed that something extraordinary had occurred, a global magnetic resonance perfectly synchronized with an interstellar object's passage, but no one could agree on why. Three main camps formed. Each offered an explanation plausible enough to sound rational, yet incomplete enough to deepen the mystery. The first, the solar coupling model, insisted the entire phenomenon was solar in origin. Proponents argued that 3IATLAS was a red herring, a coincidence of timing. To them, the pulse was a form of magnetohydrodynamic resonance triggered by internal solar oscillations. The sun, after all, constantly hums with low-frequency vibrations, acoustic and magnetic waves that travel through its plasma body and radiate into space. Under rare circumstances, those oscillations might propagate along the heliospheric current sheet and interact with Earth's magnetosphere. Supporters of this idea pointed to a subtle 7-second periodicity discovered in archival data from SOHO and SDO, both of which occasionally detect rhythmic coronal flickers. Those micropulsations, they said, could have coincided with the auroral oscillations purely by chance. The sun doesn't need an interstellar trigger, one paper in solar physics argued. It generates its own rhythms. But critics of the solar coupling model noted that such periodicities are usually short-lived and localized, rarely global, and almost never synchronized across hemispheres. The sun was unusually quiet during the event, no flares, no strong solar wind, which undermined the idea of a natural solar driver. Moreover, the magnetic waveform detected by the Parker Solar Probe didn't match known solar oscillations. Its amplitude was too strong, its coherence too clean. It looked like a response, not a source. The second camp offered the magnetospheric feedback hypothesis, a more terrestrial explanation. According to this model, Earth's own magnetic system entered an unstable feedback loop, amplifying tiny fluctuations until they became a self-sustaining resonance. It was, in essence, an auto-oscillation of the planet's magnetic shell. In this scenario, the CME that hit 3IATLAS didn't transmit energy directly to Earth. Instead, the weak perturbation it generated merely nudged the magnetosphere into one of its natural eigenmodes, a resonant frequency that can, under the right conditions, sustain itself briefly before damping out. Similar self-resonant phenomena occur in plasma chambers on Earth, where trapped fields oscillate spontaneously once externally stimulated. If true, it would mean the green pulse was a planetary echo, not an interstellar broadcast. The frequency might correspond to the fundamental field line resonance of the magnetosphere, normally too weak to notice but amplified by the exceptional calm of the solar wind that week. It was an elegant explanation until scientists ran the numbers. The damping timescale of such resonances is on the order of minutes, not days. The green pulse persisted for nearly 4 nights, reappearing each time the alignment with 3I-ATLAS's orbit renewed. No model of magnetospheric feedback could reproduce that endurance without continuous external input. That brought the debate to the third and most controversial theory: heliospheric coupling via interstellar catalyst, the idea that 3I-ATLAS itself acted as a resonant conductor within the Sun's magnetic architecture. This hypothesis, first whispered on encrypted research channels and later discussed openly at a closed ESA conference, proposed that 3I-ATLAS's metallic composition and near-perfect ecliptic trajectory allowed it to behave like a magnetic relay, temporarily linking the solar wind and planetary fields into one oscillating circuit. In simpler terms, the Sun struck a note, the interstellar object amplified it, and Earth's magnetosphere sang in tune. The mathematics, while speculative, wasn't impossible. Plasma physicists at the Keldysh Institute in Moscow modeled the interaction as a 3-body electromagnetic system: the Sun as a source, the comet as an inductor, and Earth as a resonator. Under precise conditions, alignment, low turbulence, and conductive materials, the system could sustain a standing magnetic wave for days, the predicted frequency between 0.13 and 0.17 Hertz. The match to observed data was almost exact, but this cosmic circuit model raised uncomfortable implications. If interstellar bodies could amplify magnetic energy across planetary scales, then our solar system might occasionally act like a resonant network, a vast electromagnetic organism briefly activated by passing conductors. The idea felt almost mythic, and many dismissed it as poetic nonsense. Still, the coincidences refused to fade. An even more exotic interpretation grew out of this camp: the resonant catalyst hypothesis. It proposed that 3I-ATLAS's composition wasn't just metallic but crystalline at the atomic scale, forming natural ferromagnetic lattices capable of quantum resonance. In that scenario, the object wouldn't simply conduct magnetic energy, it would store and re-radiate it at a fixed frequency, effectively acting as a giant self-tuning oscillator. Such a material, though never found naturally, could form in extreme environments like supernova remnants, where shock compression freezes metals into ordered patterns. If 3I-ATLAS originated from such a region, its lattice structure might explain the precise harmonic ratios seen in both magnetic and optical data. Still, skeptics balked. Quantum crystals from another star aren't required to explain auroras, wrote one reviewer in Nature Astronomy. We're still dealing with plasma physics, not cosmic sentience. Yet not all the alternate theories came from mainstream science. A small but vocal group of interdisciplinary researchers, atmospheric physicists, geologists, and data scientists, began probing Earth-based correlations. They noted that during the green pulse window, seismic sensors in Chile and Japan recorded faint rhythmic tremors unconnected to tectonic activity. The pattern mirrored the same 7-second frequency. Could magnetic coupling have induced mechanical vibrations through the planet's crust? Magnetostriction, the process by which magnetic fields cause materials to expand or contract, could, in theory, produce minute oscillations in ferromagnetic rock. That would suggest the pulse didn't just dance in the skies, it subtly rattled the ground beneath our feet. If so, it might have briefly unified multiple planetary systems, magnetosphere, ionosphere, lithosphere, into a single vibrating structure. The notion veered dangerously close to fringe science, yet the data points were real, and they begged for explanation. The atmospheric resonance model offered another angle. Researchers at the Finnish Meteorological Institute speculated that the rhythmic auroras could have generated secondary electromagnetic standing waves trapped between Earth's surface and the ionosphere, similar to the Schumann resonances, but much slower. Those low-frequency waves might have further reinforced the magnetic oscillation, creating a feedback loop between Earth and its surrounding plasma. Still, even that couldn't explain the precision timing with 3I-ATLAS's orbit. Eventually, in the absence of consensus, a meta-hypothesis emerged, the coincidence cascade theory. It suggested that multiple natural processes, each ordinary in isolation, happened to overlap perfectly. A calm solar cycle, an unusually conductive interstellar object, a fortuitous alignment with the ecliptic, and Earth's magnetosphere resonating at its natural frequency. No single factor was supernatural or exotic. Together, they produced an illusion of design. This became the official explanation favored by cautious agencies, the same approach used whenever phenomena defy easy categorization. Coincidences, after all, don't threaten paradigms. They simply remind us that randomness sometimes arranges itself too neatly for comfort. But even among skeptics, there were whispers. Because coincidences rarely produce phase-locked symmetry across hemispheres. They don't usually maintain coherence across millions of kilometers, and they don't generate harmonics that align with the rotation of an object hundreds of millions of kilometers away. Privately, several senior heliophysicists admitted that no existing model could replicate the full dataset. "It's not that we lack data," one said in an off-record conversation. "It's that the data describes something we don't have equations for yet." In late June, a classified cross-agency report, later leaked under the code name Project Resonant Veil, summarized the stalemate. It concluded that the green pulse could not be attributed solely to solar dynamics, magnetospheric self-oscillation, or instrumental error. It listed the probability of coincidental alignment as statistically implausible. And in one cryptic line near the end, it mentioned the possibility of an unknown coupling mechanism between interplanetary and planetary magnetic domains, potentially involving conductive interstellar debris. That was bureaucratic language for something out there connected with Earth's magnetic field in a way we don't understand. Since then, countless amateur and professional theorists have tried to close the gap. Some see 3IATLAS as an ancient relic, a fragment of a long-dead civilization's technology drifting between stars. Others believe it's entirely natural, a cosmic tuning fork that happened to ring in harmony with our world. Whatever the truth, the debate itself has become a mirror of the event, oscillating endlessly between skepticism and wonder, between science and mystery. Because when an entire planet's magnetosphere beats in rhythm with something from another star, coincidence begins to feel like the least scientific word in the language, challenges and anomalies. By the time the green pulse faded, Earth's instruments had captured enough data to fill terabytes of archives, magnetic waveforms, spectral traces, plasma readings, and auroral imagery from every major observatory. But what should have clarified the mystery only deepened it. Each dataset answered one question while opening 10 more. For every pattern that made sense, another broke all known rules of space physics. What emerged wasn't a clean scientific discovery, but a tangled web of contradictions, an event that seemed to obey and defy physics in equal measure. The first major challenge was coherence versus chaos. Space is noisy. The solar wind is a turbulent sea of plasma, its magnetic fluctuations smeared by billions of interacting particles. Natural oscillations in such an environment don't stay synchronized. They lose coherence almost instantly, especially across vast distances. Yet the green pulse remained coherent for nearly 4 days. The same clean waveform appeared in data from Parker Solar Probe, Earth-based magnetometers, and auroral photometers separated by millions of kilometers. Statistical analysis confirmed what intuition already whispered. This level of coherence was impossible for a natural plasma wave. No known process could maintain phase stability across that much space and time. It was as though the entire inner solar system had for a few days fallen into lockstep, a single synchronized system behaving like one resonant body. The second anomaly concerned phase alignment. Every instrument that recorded the pulse showed identical timing down to fractions of a second. Northern and southern hemispheres mirrored each other perfectly with zero measurable lag. Even signals passing through different layers of Earth's magnetosphere, from high-altitude satellites to ground-level observatories, remained in phase. Normally, propagation delays through plasma layers introduce phase shifts measurable in milliseconds or more. Here, there were none. One team at the Finnish Meteorological Institute tried to model how such simultaneity could occur. Their conclusion, it couldn't. Even if a magnetic wave struck the planet uniformly, Finite transmission speeds through Earth's magnetic field would cause measurable phase drift. The only way to synchronize all detectors perfectly was if the magnetic field itself were being modulated uniformly, as if an external field enveloping the planet oscillated everywhere at once. The next problem involved signal purity. When plotted as a frequency spectrum, the green pulse appeared almost too perfect, a narrow, clean spike at 0.15 Hz with secondary harmonics at exactly double and triple that frequency. No natural magnetic fluctuation in the solar wind has ever exhibited such precision. Typical Alfvén waves spread across broad frequency bands. Even man-made electromagnetic interference, like power grid harmonics, displays more variation. This was surgical, a line so sharp it looked engineered. That purity made error checking crucial. NASA and ESA teams immediately launched a joint review to rule out instrumental contamination. Could the satellites have picked up a calibration artifact, perhaps a rhythmic error in onboard electronics? The answer was a resounding no. Independent magnetometers, some built by entirely different agencies using different sensors and time references, all recorded the same pattern. Even retired instruments, like Japan's Akabono satellite reactivated for testing, showed identical readings. The odds of multiple independent systems scattered across orbits and agencies, all producing the same false signal, were infinitesimal. Then came the energy paradox. Magnetic field oscillations of the observed amplitude required enormous input power. Calculations estimated the total energy involved at roughly 10^17 joules, equivalent to 100 megatons of TNT. That energy didn't come from solar wind, which remained steady and weak throughout the event. No energy spikes were detected entering the magnetosphere from the usual directions. Yet the oscillation persisted, sustained as though powered from an invisible source. The logical conclusion was that energy had entered Earth's magnetic system through non-traditional means, perhaps coupling through the heliospheric current sheet or through the very geometry of the field itself. But when physicists attempted to trace power flow through magnetohydrodynamic MHD models, the math broke. Energy seemed to appear inside the system without passing through its boundaries. That's not just a puzzle, it's a violation of conservation principles as currently understood. The anomalies didn't stop at magnetism. Atmospheric scientists noted subtle disturbances in the ionosphere, the layer of charged gas that forms Earth's upper atmospheric shell. During the pulse, ion density oscillated in rhythm with the magnetic beat. This was expected, but temperature fluctuations within the layer didn't match magnetic intensity. In some regions, temperatures dropped when magnetic strength peaked, a reversal of standard thermodynamic behavior. It was as if the upper atmosphere were alternately heating and cooling in ways that ignored the normal energy flow from the sun. That led to speculation about unknown particle interactions. Could the pulse have carried high-energy particles that momentarily changed the ionosphere's chemistry? Or perhaps, as one daring researcher suggested, the oscillation affected electron spin alignments on a quantum scale, an interaction bordering on the metaphysical in its implications. A separate set of anomalies arose in Earth's radio environment. During the pulse, ground-based VLF, very low frequency, transmitters detected rhythmic sidebands, faint echoes that modulated around the same 0.15 Hz frequency. Radio astronomers at Stanford confirmed that these sidebands were global, occurring simultaneously across multiple frequencies. Nothing in human-made communications or space weather phenomena could account for their uniformity. When converted to audio, the signal produced a strange, almost melodic pattern, a repeating tone with faint subharmonics, eerily similar to the pulse sequence seen in magnetometer data. Another challenge came from the duration discontinuity. The pulse didn't fade gradually. It started abruptly and ended the same way, as though switched on and off. Every global magnetometer recorded the same instant of termination, 0217 UTC on May 9th, down to the same second. That simultaneity, too, is unnatural. Even when geomagnetic storms subside, their decay is exponential, not instantaneous. The green pulse behaved like a transmission. A carrier wave terminated with mathematical precision. More anomalies emerged when the final oscillation was analyzed. Hidden within the waveform's last few cycles was a phase inversion, the same reversal noted by the swarm satellites. In signal processing, such inversion is typical of a reflection, when an outgoing wave bounces off a boundary. But what was Earth reflecting? The surrounding plasma density hadn't changed. No solar event was present to bounce the signal back. The implication was unavoidable. The source of the oscillation had detected the planet's resonance and responded. The challenge wasn't just explaining what the data showed, but deciding which data to trust. Each instrument had its own quirks, its own calibration standards. So NASA created a composite waveform using synchronized datasets from 29 independent stations. When superimposed, the waveforms matched within 1/10 of a degree of phase difference. Unprecedented agreement for global measurements. It wasn't just consistent, it was identical. Even the Earth's natural Schumann resonances, normally dominant at frequencies of 7.8, 14, and 20 Hz, displayed faint side modulation in harmony with the pulse. It was as if the entire electromagnetic environment of the planet had been enveloped by a slow, rhythmic modulation from beyond. Another oddity emerged months later, when geophysicists analyzed seismic data. Deep borehole sensors in Japan and Chile, far from tectonic boundaries, recorded minute vertical oscillations during the event. The motion matched the magnetic cycle frequency exactly. Though too weak to feel, the tremors indicated that the electromagnetic pulse may have coupled mechanically to Earth's crust, a feat previously thought impossible at such low amplitudes. Perhaps the strangest anomaly, however, was the missing data gap. For approximately 9 minutes on May 8th, several satellites, including Themis D and Cluster 2, reported temporary telemetry dropout. Their onboard clocks kept running, but data streams froze. When transmission resumed, the internal timestamps were perfectly aligned, as if the systems had experienced a synchronized blackout. Engineers suspected software errors or solar interference, but logs showed no technical faults. Whatever caused the pause affected multiple spacecraft simultaneously. It became known informally as the blackout interval. Some speculated it represented the peak of the resonance, a moment when the entire local magnetic environment saturated, temporarily overwhelming sensors. Others went further, suggesting it might mark a transient alteration of space-time conditions near Earth's magnetosphere, a kind of localized field distortion. That idea remained fringe, but it reflected the growing realization that classical physics alone couldn't explain what had happened. The final challenge was interpretive. Scientists could describe the how, oscillations, harmonics, timings, but not the why. Every attempt to simulate the event required bending known laws. If energy came from the sun, it lacked the expected signatures. If it came from 3IATLAS, it traveled impossibly far. If it originated locally, it behaved as though orchestrated by an external conductor. The anomalies forced researchers to confront uncomfortable possibilities, that the solar system is threaded by resonant magnetic structures we've never mapped, that interstellar objects can act as amplifiers or catalysts for field interactions, or that, under rare alignments, space itself may sustain organized oscillations, magnetic standing waves capable of linking worlds. In the end, the green pulse didn't just reveal strange data, it exposed a blind spot in human understanding. The magnetosphere, long viewed as a defensive shield, had proved to be something far more dynamic, a resonant membrane capable of singing when struck by the right frequency. And though the event ended, its anomalies remain unresolved. Echoes of a pattern too precise for chance, too persistent for error, and too vast for comfort. A cosmic rhythm that appeared once, demanded to be noticed, and then disappeared, leaving behind a riddle written in magnetism that Earth, for now, has no language to answer. Implications and what it suggests. When the green pulse finally faded from Earth's skies, it left more than shimmering auroras and terabytes of data. It left a wound in the story science tells about how the universe behaves. For centuries, we've believed that cosmic forces, vast and indifferent, move according to fixed principles: gravity, magnetism, entropy. They do not synchronize with one another, and certainly not with the heartbeat of a single planet. Yet, for 4 days in May 2025, the data suggested otherwise. The immediate implications were both thrilling and disquieting. For one, the event proved that magnetic coherence across interplanetary distances is not only possible but can persist in stable resonance. This challenged the long-standing assumption that magnetic waves dissipate chaotically across solar plasma. Instead, it hinted at an invisible architecture of order: filaments, corridors, or standing wave structures through which magnetic energy can travel intact, almost as if the solar system itself were threaded by harmonic channels. If those channels exist, it means our heliosphere is not a random bubble of solar wind, but a resonant cavity, a kind of electromagnetic instrument capable of amplifying or storing energy when the right frequencies are introduced. The passage of 3IATLAS may have simply struck the chord. Such a concept isn't entirely alien to physics. In plasma cosmology, magnetic fields can self-organize into Birkeland currents, colossal strands of current stretching across space, capable of carrying structured energy. In Earth's upper atmosphere, smaller versions of these currents form the auroras themselves. If the heliosphere contains similar filaments, they could act as waveguides, channeling energy from distant disturbances directly into planetary magnetic fields. This would mean that the sun, planets, and even interstellar visitors are part of a single connected system, a magnetically entangled architecture operating at scales far larger than we currently model. The implications for heliophysics are profound. Space weather, once thought to depend solely on solar activity, may also be influenced by these hidden resonances. Planetary alignments, cometary intrusions, and even interstellar dust flows could subtly modulate the entire solar magnetic environment. In other words, the cosmos might not be a chaotic storm. It might be orchestrated, at least in part, by resonance. For astrophysicists, the next question was obvious. If such resonance can happen once, can it happen again? And if so, what are the conditions that allow it? Data reconstruction suggested several prerequisites. The first was geometric alignment. Sun, Earth, and the interstellar object must all share a near-perfect magnetic axis. The second was plasma stillness, low solar wind turbulence, like a calm ocean before a sound wave. The third was conductive catalyst, a metallic or magnetically active body, 3IATLAS in this case, capable of reflecting or focusing the solar magnetic field. These three ingredients, when combined, produced something no one anticipated: Earth's magnetosphere acting as an antenna tuned to a cosmic frequency. This realization led to a startling possibility that our planet may occasionally listen to space in ways we've never recognized. The magnetosphere might not merely defend against radiation, it might also act as a receiver, resonating with low-frequency signals that originate far beyond the sun. If that's true, then the 2025 event could represent the first documented instance of interstellar magnetic communication, not intelligent in the conventional sense, but physical, the universe speaking to itself through structured fields. Some scientists embraced this interpretation cautiously, describing it as field coupling on cosmic scales. Others shied away, unwilling to risk their reputations on a phenomenon that brushed too close to metaphysics. But the phrase that began circulating among heliophysicists captured the awe and unease perfectly. The universe hummed, and Earth replied. Beyond astrophysics, the implications reached into geophysics and biology. Magnetic fields are not abstract lines on a chart. They shape how radiation interacts with the planet, how the ionosphere behaves, even how migratory species orient themselves. During the Green Pulse, magnetometers in the Arctic recorded directional errors in animal tracking sensors. Birds deviated from migratory paths. Whales altered course mid-ocean. These weren't catastrophic disruptions, just subtle deviations, as though the compass of life itself had briefly swayed to a different rhythm. If such events recur, even rarely, they could imprint faint but lasting signatures in biological systems, a kind of environmental magnetic memory. The planet might record cosmic rhythms in DNA, in sediments, in isotopic anomalies. That idea, once fringe, is now being revisited with fresh seriousness. The pulse also carried implications for human technology. During its peak, power grids in Canada and Scandinavia logged unusual harmonics in current flow, though no damage occurred. Satellite communications briefly desynchronized before recovering. The event was too weak to cause harm, but it proved that global infrastructure, much of which depends on the magnetosphere for protection, can respond to even subtle cosmic modulations. If such resonances can be predicted, they could provide early warnings for solar weather-like disturbances that don't originate from the sun at all. Conversely, if they cannot be predicted, they represent a new kind of environmental hazard, a magnetic resonance storm that can appear without warning, independent of solar cycles. The theoretical implications were even more unsettling. In physics, coherence on planetary scales implies information transfer, not in the sense of communication by intent, but in the sense that systems are exchanging organized energy. The green pulse demonstrated that information, encoded as magnetic oscillations, could travel across interplanetary space with negligible loss. That revelation reframed how some scientists view interstellar phenomena. Could pulsars, quasars, or magnetars emit structured magnetic waves that resonate with planetary fields across light years? Could life-bearing worlds be subtly synchronized with these cosmic beats, their atmospheres and magnetospheres modulating in response? It's a speculative thought, but so was planetary magnetism, once. One quiet paper, circulated through ESA's internal network, suggested a radical new concept, heliospheric memory. It proposed that the sun's magnetic field might preserve traces of interactions with passing bodies, much like ripples trapped in frozen water. Each interstellar object that crosses its current sheet could leave behind a faint, resonant fingerprint, an echo signature embedded in solar plasma. If true, studying those echoes could reveal a hidden history of cosmic visitors, recorded not in rock or light, but in magnetism. That would transform how we study the cosmos. Instead of relying on telescopes to catch fleeting sightings of comets and asteroids, we could listen to their magnetic aftermath, reading the solar system's field like a phonograph etched by passing stars. Still, the implications go deeper, into the realm of philosophy. The green pulse blurred the line between cause and effect. Was Earth's magnetosphere responding to an external force, or was it part of a self-organizing resonance that required its participation? The distinction matters because it defines the planet's role in the cosmic system. If passive, we were spectators. If active, we were participants in a universal network of fields, each celestial body a node in an ongoing dialogue of magnetism. Some thinkers have drawn parallels to ancient cosmologies where the heavens were described as music, spheres producing tones that harmonized into existence itself. The Greeks called it musica universalis. Today's physicists might call it field resonance theory. Different language, same intuition, that the universe doesn't just move, it vibrates. Perhaps the most humbling implication is what the event says about human limitation. For decades, our instruments stared at the stars, searching for visible signals, light, radio, gravity. Yet the most profound connection we've ever detected came not in light or sound, but in magnetism, the quiet architecture beneath reality's surface. We weren't looking for it. It found us. In the aftermath, international agencies quietly began developing new detectors capable of measuring ultra-low frequency magnetic variations at interplanetary scales. A network called Project Chorus was proposed, an array of magnetometers stationed on Earth, the Moon, and Mars, designed to detect any future coherent magnetic events. If another interstellar body passes through the heliosphere, they hope to be ready. Because for all its beauty, the green pulse raised one question that refuses to fade. What if it happens again, but stronger? If the event was a one-time resonance, it's a marvel. But if it represents a periodic phenomenon, tied to the cycles of the sun or the trajectories of incoming interstellar objects, then we are witnessing the first hints of a larger pattern, a cosmic heartbeat that's always been there, waiting for us to notice. And if that's true, it changes everything. It means the solar system is not an isolated mechanical system, but part of a living electromagnetic continuum, one that spans from the sun's core to the edge of interstellar space. It suggests that space itself may be less a void and more a medium of resonance, a cosmic sea through which frequencies of unknown origin occasionally sweep, momentarily synchronizing worlds before fading back into silence. For a few days, Earth was part of that song. We felt the rhythm ripple through our magnetic veins, saw it painted across our skies, measured it in our machines. And though the pulse has vanished, the implication remains that somewhere in the vastness, something out there can still find our frequency. And when it does again, the question won't be whether we can explain it, it will be whether we're ready to hear what it's saying. Unanswered questions and open paths. When the green pulse ended, silence returned to the magnetosphere, but not to the minds of those who had watched it happen. Across every observatory, lab, and control room, one feeling lingered: the sense that we had glimpsed something vast, fleeting, and far beyond our current understanding. For 4 nights in May 2025, Earth had been drawn into rhythm with an interstellar object. The data was irrefutable, but what it meant, that remains the single greatest mystery of our age. Even now, months after the event, scientists and philosophers alike are still sifting through the debris of explanation. Each dataset, once thought complete, raises new and uncomfortable questions. Some are technical, some are existential, and none have simple answers. The first question is causality. Did 3IATLAS cause the green pulse, or did it merely coincide with it? Causation is the foundation of science, but in this case, it dissolves under scrutiny. The timing was perfect, the alignments flawless, the signatures synchronized, and yet every attempt to mathematically link the interstellar object's physical output to the power observed in Earth's magnetosphere comes up short. There was no direct energetic path strong enough to drive the resonance. The comet emitted light, dust, and plasma, but not enough to influence a planet 150 million kilometers away. So where, then, did the energy come from? Some believe the answer lies in field coupling, the idea that objects sharing a magnetic environment can interact through the field itself, without exchanging matter or energy in the conventional sense. But this concept, while grounded in plasma physics, has never been observed at such scale. If it's real, then space is not empty. It's an active medium through which structured magnetic patterns can propagate like sound through air. That realization leads to the second great question: was the resonance unique or part of a larger pattern? If the heliosphere can act as a resonant chamber, then the green pulse might not have been a singular event, but the latest occurrence in a much older cycle. Researchers have begun combing through historical magnetometer records, some dating back to the 19th century. A few anomalies stand out. In 1872, for instance, magnetic observatories recorded rhythmic oscillations during the Great Auroral Storm, oscillations later dismissed as instrument drift. In 1940, Antarctic stations noted a repeating 0.16 Hz variation during a week of low solar activity. Even the Carrington event of 1859, once thought chaotic, contained faint rhythmic modulations buried in the noise. Could these be ancient echoes of the same phenomenon, the heartbeat of a system that occasionally finds its own frequency? If so, what triggers it? Are interstellar objects like 3IATLAS the catalysts, or merely participants in a process far larger than any single visitor? The third question ventures deeper into philosophy. What is resonance, truly? In classical physics, resonance is simple, an amplification of oscillation when frequency and system align. But in the context of the green pulse, resonance seemed to bridge boundaries that should be impermeable: interplanetary distances, magnetic domains, even matter and consciousness. Some have speculated that resonance might represent a universal organizing principle, a mechanism by which complexity emerges from chaos. The same way electrons orbit at quantized energy levels, perhaps magnetic systems, too, can fall into discrete states of harmony. If that's true, then the universe isn't a void punctuated by random collisions. It's a symphony of frequencies occasionally overlapping, briefly harmonizing before drifting apart again. That leads to the fourth question: did Earth respond? At the peak of the event, the final pulse detected by the swarm satellites showed a reversed phase, a reflection. It looked, mathematically, like an outgoing signal. Some dismissed it as rebound noise, but others weren't so sure. If the Earth's magnetosphere acted as a resonant cavity, then energy could have been reflected, not merely absorbed. But what if it wasn't reflection? What if the resonance forced the magnetosphere into coherence, and that coherence generated an outgoing signal naturally, the way a vibrating string produces an overtone? If that's true, then the Earth may have emitted a field structure, a reply, not in words, but in magnetism. That possibility redefines our relationship with the cosmos. We are not passive recipients of celestial events, we are part of a two-way conversation. The fifth question is whether life noticed. Biological systems are deeply sensitive to electromagnetic fluctuations. Migratory species navigate using magnetic fields. Human brains emit faint rhythms that can, in theory, entrain with external signals. During the pulse, small anomalies were recorded in human Schumann resonance experiments, subtle shifts in the brainwave frequencies of volunteers who were asleep during the event. Nothing conclusive, but the suggestion remains. The entire biosphere may have felt, however faintly, the universe's rhythm. If so, what does that mean for evolution, consciousness, or the nature of awareness itself? Could life, which depends on magnetic molecules like iron and hemoglobin, be more responsive to cosmic resonance than we realize? Could civilizations in other systems experience their own versions of the green pulse and interpret them through myth, religion, or science, depending on their level of understanding? That speculation raises another open path: interstellar intelligence, not in the traditional sense of radio beacons or probes, but as a network of resonant entities communicating through the medium of magnetic fields. If space can transmit organized oscillations, then perhaps advanced civilizations long ago discovered how to encode information not in photons or particles, but in field harmonics. What we experienced may not have been intentional, but it could reveal a universal method of communication we've been too technologically primitive to recognize. The sixth question is one of prediction. Can the next resonance be forecast? Teams at NASA's Project Chorus and ESA's Solar Magnetodynamics Division are now working to identify pre-resonant conditions, periods when the heliosphere's magnetic geometry becomes especially symmetrical. Using models of the heliospheric current sheet, they've identified several potential windows over the next decade when similar alignments could occur, especially during solar minimum, when turbulence is lowest. Each represents an opportunity or a warning. But even if another resonance does occur, we may not recognize it immediately. The 2025 event only became obvious because Earth happened to be at the right angle with a magnetosphere tuned to the same frequency. The next one could involve Mars, Venus, or even Jupiter, all magnetized worlds, each capable of their own unique resonant modes. If the green pulse was only one part of a larger heliospheric symphony, we may have heard just a single note. Another open path involves energy applications. If resonance coupling can transfer magnetic energy across space without direct physical connection, it could revolutionize how we understand propulsion and power. Imagine spacecraft designed to surf magnetic waves between planets, or to harvest energy from heliospheric oscillations without fuel. Though purely theoretical, the underlying physics, field coherence, resonance amplification, energy transfer, is already under study in plasma laboratories. What began as a cosmic mystery might someday become a technology. Yet all of this leads to a final humbling question: why now? Interstellar objects have entered our system before: Oumuamua in 2017, Borisov in 2019, others unrecorded. None triggered anything like this. Why did 3IATLAS specifically resonate? Was it its composition, that nickel-rich metallic lattice capable of conducting magnetism? Its trajectory, nearly aligned with the ecliptic? Or was it timing, arriving during a rare moment of solar stillness when the sun's field was calm enough to transmit the signal cleanly? If all three conditions aligned perfectly, it could mean that such events occur only once in centuries, fleeting harmonies between sun, planet, and visitor. But if 3IATLAS was simply the first we noticed, then others may have come and gone, their resonance is lost in the noise of solar storms. In that sense, the unanswered questions become a map, a set of open paths leading forward. Future missions, magnetometers on the moon, solar probes in interstellar space, ground networks scanning the lowest frequencies of the spectrum might someday catch the next resonance in real time. But some paths lead inward, not outward. The green pulse forced us to confront our own assumptions about separation. We've long believed ourselves isolated, a world orbiting an ordinary star, bound by physical laws that keep us apart from the greater cosmos. Yet for 4 nights, that illusion broke. The magnetic heartbeat of another object touched ours, and for a moment, we weren't alone. We were part of something, a hidden architecture that ties worlds together not through gravity, but through rhythm. And that may be the greatest unanswered question of all. Is resonance simply physics, or is it the universe's way of remembering itself? Perhaps, as some quietly suggest, the green pulse was not a message to decipher, but a reminder that every star, every planet, every drifting stone between them, all are instruments in a single cosmic orchestra. Most of the time, they play in silence, but once in a great while, when alignment, composition, and timing find harmony, the music returns. We call it a coincidence. The universe calls it continuity. And somewhere beyond the reach of light but not of field, 3-eyed Atlas is still moving, a fragment of another world fading into interstellar night, carrying perhaps the faintest echo of the song it briefly taught us to hear.